across the ruins of ancient cities, in the silent vaults of forgotten workshops, and beneath the ash of civilizations long vanished, objects of astonishing ingenuity once existed, and then disappeared. Mechanisms that predicted the stars, metals that rivaled steel, glass that could bend without breaking, and pigments that outshone the sun all hint at knowledge the world has lost. From the shores of Greece to the deserts of Egypt, through the courts of Rome and hidden corners of distant empires, fragments of these vanished inventions endure, tantalizing and enigmatic. The journey through these stories unfolds on screen, tracing the echoes of brilliance and secrecy that allowed these creations to vanish from the record books, leaving only the faintest traces for those who seek them. The Antikythera mechanism. When the sponge divers of Symi surfaced off the small Greek island of Antikythera in 1900, they expected nothing more than a season's harvest of sea sponges. Instead, tangled among coral and bronze statues, they found fragments of something that did not belong to the ancient wreck's mythic cargo. It was a compact cluster of corroded bronze gears fused into a lump of green stone. No one on the deck understood what they were seeing. The sea had claimed the ship over 2,000 years earlier, but this object, with its interlocking cogs and precise engravings, hinted at knowledge that should not have existed in that age. The fragments were taken to Athens, where they languished for years in the National Archaeological Museum. Scholars catalogued them alongside amphorae, coins and statuary without realizing what they truly were. The bronze seemed ordinary, until the light struck the edges of the corroded metal, revealing gear teeth carved with astonishing uniformity. When the first researchers noticed Greek inscriptions running along the edges, faint and deliberate, the mystery deepened. Ancient Greece was known for philosophy, for art and geometry, but not for machines that imitated the heavens. In 1959, British physicist and historian Derek J. de Solla Price began a systematic study of the fragments, combining X-ray imaging with painstaking mechanical analysis. What emerged from his decades of work was beyond all expectation. The Antikythera mechanism was a geared analog computer, constructed sometime between 150 and 100 BCE. It could predict the positions of the sun, moon and planets, chart lunar phases, and forecast eclipses with a precision that rivaled instruments not built again for more than 1,000 years. 37 gears once turned in harmony inside a wooden casing roughly the size of a shoebox, driven by a single hand crank that set the cosmos in motion. Price called it a mechanical computer that appears suddenly and without any antecedents. He was right. No earlier example of such gearing had ever been found. The complexity implied a tradition of craftsmanship and mathematical understanding that history had somehow erased. It forced archaeologists to reconsider what the ancient world might have achieved and how much had been lost. Later imaging in the early 21st century, using advanced X-ray tomography, revealed additional inscriptions that transformed understanding further. The markings were not decorative but instructional, describing cycles of planets, the colour of eclipses, and even athletic calendars linked to ancient games. The device's back panel contained twin spiral dials, one tracking the 235-month Metonic cycle, the other the 223-month Saros cycle used to predict eclipses. Its front face displayed the zodiac and a small ball representing the moon, half black and half silver, rotating to show its changing phases. These details were not symbolic. They were mechanical astronomy rendered in bronze. No record survives of who built it. Theories point toward the island of Rhodes, where scholars like Hipparchus once mapped the stars with instruments now lost. The mathematics behind the gearing align with his lunar theories, suggesting his influence, if not his direct hand. But the mechanism's craftsmanship implies a team, metalworkers, mathematicians and astronomers, all operating within a forgotten tradition of scientific instrument making. If so, it means ancient Greece once possessed an entire discipline that vanished without a trace. The shipwreck that preserved the fragments may have been carrying them from Rhodes to a wealthy patron or scholar in the Roman world. The wreck's cargo, bronze sculptures, glassware, luxury goods, suggests a private collection being transported when a storm forced the ship against the rocks. The mechanism sank with it, sealed beneath the seabed for 2 millennia, its wooden case disintegrating, its gears slowly welded together by time. Modern reconstructions, based on CT scans and digital modelling, show that the mechanism's precision rivaled that of 17th century clockwork. Each gear tooth was cut by hand to fit into ratios derived from astronomical cycles known only through advanced observation. It was not an experiment, it was the product of refinement, the culmination of methods honed over generations. Yet no workshop, no text, no second example has ever been found. It stands entirely alone, an orphaned invention whose predecessors and successors were erased from history. How such a tradition could vanish is a question that continues to haunt historians. The fall of Greek city-states, the Roman absorption of Hellenistic knowledge, and the fragility of bronze itself all played a part. Machines of such intricacy could have been melted down for weapons or lost in fires that consumed libraries and workshops. Knowledge may have been considered sacred or secret, guarded by astronomer engineers whose craft died with them. What remains is only a relic, a single surviving echo of an invisible lineage. Even now, despite decades of study, there are functions no one fully understands. Some fragments suggest additional gears that tracked planetary motions, possibly even the movements of Mercury and Venus relative to Earth. The missing pieces hint that the mechanism might once have displayed the entire known cosmos in motion, a miniature universe enclosed in wood and bronze. The more scholars reconstruct, the clearer its sophistication becomes, yet the greater the void of its origin. The Antikythera mechanism stands at the intersection of science and myth, a real machine from an age when such things should not have existed. It rewrote what was believed possible for the ancient world, forcing historians to confront how much knowledge can disappear without leaving a trace. Beneath its corroded surface lies a silent accusation that civilization once reached heights of mechanical genius and then forgot. And somewhere in that forgotten lineage of minds, the secret of the stars was written in gears and lost to the sea. Damascus steel. Under the dim glass of the Topkapi armory, the blade still breathes light. The rippled surface of a Damascus sword catches and bends the museum lamp into ribbons, and visitors imagine a temper more myth than metallurgy. The pattern seems to move, to flow like water frozen mid-current, and that illusion is the first proof that this is not ordinary iron but the remnant of a vanished chemistry. The blade's surface is not a painted design but the outcome of crystalline structures and deliberate thermal work, a record written in carbide bands and folded grain that no surviving smith can now fully explain. In that hush, history feels tactile and immediate, as if the metal still remembers the hands that struck it. For centuries these blades crossed empires. Crusaders carried tales of swords that cleaved mail and musket barrels. Persian chroniclers praised edges that kept their keenness through campaign and ceremony alike. By the early modern period, the term Damascus had gathered legend around it, and every man's shorthand for a perfect sword, yet trade records and travellers' accounts point elsewhere for the metal's origin. Wootz ingots from South India, exported along Indian Ocean routes to Syrian forges where craftsmen fashioned finished blades. That route of commerce, traced in port registries and merchant letters, implies a chain of knowledge spanning workshops, shipyards and market stalls, a geography of craft now severed from living memory. Yet the secret lay not in the shape of the blade, but in its very blood, its metal. The raw material known as Wootz was produced in small, sealed crucibles, where iron and carbonaceous additives were melted into a high-carbon steel that solidified into patterned ingots. Microscopy of surviving samples reveals bands of cementite and alloy carbides arrayed in distinct, sometimes dendritic patterns. Some modern analyses report layered carbides and structures that suggest nucleation around trace elements. Those microstructures are the fingerprint of a process that married chemistry and thermal control, and the visible surface pattern is merely the outward voice of an inner metallurgy whose precise conditions, temperature curves, fluxes and fuel, are lost to history. Somewhere in the late 18th century, the fires went out. The age when true Damascus blades were commonplace gave way to a world of pattern-welded imitations and industrial steels, and with shifts in trade and political power, the artisans who once worked those ingots vanished into obscurity. Colonial disruptions severed markets, new smelting methods displaced small crucible operations, and the specific ores and organic additives that may have contributed to the Wootz microstructure became harder to obtain or simply ceased to be used. The result was not a sudden catastrophe, but a slow unweaving. Recipes fell out of family memory, workshops closed, and the living thread that connected riverbank furnaces to Syrian anvils frayed until it snapped. Modern metallurgists have tried to summon the secret back from the forge. Laboratory reconstructions in the 20th and 21st centuries have recreated aspects of the microstructure by controlling carbon content and thermal cycling, and experimental smiths have produced steels that emulate the surface pattern. Scholars such as those who published metallurgical studies on historic samples have reported nanotube-like carbon structures and aligned cementite filaments in some Wootz specimens, findings that suggest a remarkable, if unintended, nanostructural sophistication. Yet every successful laboratory blade carries an asterisk: replicated conditions, modern instruments, and assumptions about inputs that cannot be confirmed against a continuous oral or written tradition. Some say the loss was no accident. Beyond simple economic and technological change, there are accounts of guarded guilds and trade secrets jealously protected from prying rivals. There are plausible proposals that certain ores rich in trace vanadium or other alloying elements gave original Wootz its peculiar qualities, and that depletion or changed access to those deposits altered outcomes irreversibly. Other theories highlight the fragility of small-scale craft in the face of imperial expansion. When centralized powers prefer uniform, castable iron for cannon over the delicate alchemy of crucible steel, specialized smelters are often the first to be repurposed. These are not conspiracies, but likely vectors of loss, a constellation of economic, environmental, and social shifts that together extinguished a technical tradition. The name Damascus survives, but the meaning has thinned like watered ink. Today, Damascus often denotes any patterned steel, whether produced by modern pattern welding or by purpose-built alloys that imitate the original look. Museums display labelled swords whose provenance is secure and others whose histories are tangled with later repairs and restorations. Collectors prize original Wootz blades, and metallurgical labs argue over which specimens retain authentic microstructures. The word has become an echo, a linguistic relic that hints at a material reality broader and more particular than the popular imagination allows. In the highlands near Srinagar, old families still whisper of black ingots that sang when struck. Archaeological digs and metallurgical surveys in South India and Sri Lanka have located furnace remains and crucible fragments consistent with early crucible steel production, and local oral histories preserve names for processes and materials that intersect with those finds. Those valleys and river plains hold the geological sources and cultural contexts where Wootz was born, and the faint continuity of place offers a different kind of evidence. Not a continuous craft practiced without interruption, but a landscape that once supported it with fuel, ore and human knowledge arranged in ways now hard to reconstruct. Every surviving blade is a question pressed into steel. Each sample invites another line of inquiry about trade routes, about fuel and flux, about the chemistry of ores and the contours of social life that sustain rare crafts. And the more science reveals about structure and composition, the more evident becomes what has been lost. Not merely technique, but the living networks that made technique possible. Only ash remains above the buried forges, yet deep below the metal endures, holding to a memory that refuses to fade. Roman concrete. In the shadow of Roman ruins, the stone still resists time. The arches stand unbroken against centuries of rain and tremor. The harbours hold their shape against salt and tide, and the monuments of a vanished empire seem immune to the quiet erosion that devours modern cities. Engineers measure and compare, puzzled by the resilience of walls raised before the calendar we follow had even begun. Each fracture, each scar, tells of earthquakes, floods, and invasion, yet the material endures. It is as if the Romans had found a way to turn mortality itself into matter. Rome built not only cities, but a kind of permanence. Its builders filled the Mediterranean world with theatres, baths, and aqueducts, binding provinces together through a shared language of stone. Even now, the dome of the Pantheon, completed under Hadrian, stands without reinforcement, a seamless hemisphere of concrete that still holds the world's largest, unreinforced span. In harbours like Kosa and Baiae, marine structures survive where modern concrete crumbles, the piers solid after 2,000 years beneath the sea. To the Romans, this was not alchemy but mastery, an art so common it was left unrecorded, its perfection taken for granted until it disappeared. At the heart of every surviving wall lies a puzzle in powder and ash. Modern concrete, made of Portland cement, fails within decades, its steel reinforcements corroding, its surface spalling into dust. Roman concrete, by contrast, strengthens as centuries pass. Samples cut from ruined vaults reveal a dense, stone-like cohesion, as if time has worked in its favour rather than against it. The secret of its endurance was buried with the empire, scattered among fragments of Latin treatises and ruins that whisper of a knowledge no architect can now fully restore. Their mixture of lime and volcanic ash was no accident of geography. Pozzolana, a fine ash found near the Bay of Naples, was blended with quicklime and fragments of stone, sometimes with seawater or crushed pottery. The result was a material that reacted chemically rather than simply hardening by drying. Ancient authors such as Vitruvius described the process in passing, noting that certain sands made under the influence of fire could set underwater, yet the subtlety of proportion and treatment was never fully written down. What remained in text was the skeleton of a method. What lived in practice vanished with the masons who understood it by instinct and flame. Modern microscopes have peeled back layers of ancient mortar. In laboratories, fragments of Roman concrete reveal formations unseen in their modern descendants. Crystalline minerals that grow within the mix, sealing cracks and binding particles together. Researchers have identified rare structures like a luminous tobermorite, formed at low temperatures over long periods, whose crystals strengthen rather than weaken with age. In 2023, a study uncovered limeclasts, small, unreacted nodules of quicklime that seemed to serve a purpose beyond imperfection. When water entered a crack, it dissolved part of the clast, creating new minerals that filled the fracture. The material was, in effect, alive, capable of healing itself. The fall of the empire scattered more than legions. As trade routes collapsed and workshops closed, the precise sources of volcanic ash and the subtle ratios of lime to aggregate were forgotten. Medieval builders, faced with different soils and demands, replaced the Roman mix with simpler mortars. By the time industrial cement rose in the 19th century, the old ways had long since vanished, replaced by formulas of speed and uniformity. The world rebuilt itself in the image of efficiency, not endurance. What had once been a living chemistry became a lost art dismissed as primitive. Archaeologists studying ancient harbour ruins have begun to piece together the lost craftsmanship through direct excavation rather than theory. At sites like Portus Cusanus and Pozzuoli, submerged breakwaters have yielded intact cores of Roman concrete, their inner structures preserved by seawater. Analyses show that the interaction between volcanic ash and salt water triggered a long-term reaction that continues even today, producing rare minerals such as philipsite and altobermorite within the matrix. These discoveries suggest that the Romans, knowingly or not, created a material designed to grow stronger within the very element that should have destroyed it. Each recovered fragment reads like a diary of controlled chemistry written in stone, a slow dialogue between human intention and the sea. When cracks form, the material appears to awaken. In coastal ruins exposed to tides, fissures that once marked decay now show veins of new minerals knitting the gaps. Scientists studying these reactions find evidence of ongoing hydration, a process that feeds on exposure rather than fears it. To imagine such resilience in the hands of ancient builders challenges every notion of technological progress. How could a civilization without modern tools produce a concrete that improves with time while ours disintegrates? Each finding deepens the mystery rather than resolves it, revealing not a single lost recipe but an entire philosophy of material that sought harmony with nature instead of defiance of it. Perhaps the true secret was philosophical rather than chemical. The Romans built with an understanding that strength came from imperfection, from the ability to adapt and reform under stress. Their concrete absorbed damage, transformed it, and survived through change, a reflection perhaps of the empire itself in its long, uneven persistence. Modern engineers can recreate the composition, even simulate the crystalline structures, yet something remains absent. The sensibility that saw permanence not as rigidity but as resilience. Within the rough texture of every surviving wall lies a message about patience, time, and the humility of design that works with decay instead of against it. Through every remaining arch, the empire exhales faintly, its presence preserved in the weight of the stone. Greek fire. At the centre of the Byzantine Empire, when the Eastern Mediterranean was a crossroads of faith, trade and war, a weapon emerged that defied comprehension. Chroniclers spoke of flames that clung to water, of ships that burned even as they sank, and of enemies who fled not from men but from an element that behaved as if alive. The Byzantines called it liquid fire, a creation so fiercely guarded that its very formula vanished with the empire that once wielded it. Centuries later, the term Greek fire would echo through history, not as a weapon but as a riddle that refused to die. Historians have long traced its origins to the reign of Emperor Constantine IV, when the empire stood on the brink of ruin. The Arab sieges of Constantinople brought the Byzantine navy to the edge of defeat, until a man from Heliopolis, Callinicos, arrived with a formula said to summon fire from the sea itself. Ancient manuscripts describe copper siphons mounted on the prows of ships, spewing liquid that ignited mid-air and clung to wooden hulls like molten resin. Though the empire's records are sparse, those who witnessed its fury wrote of a substance that roared like thunder and burned like judgment. Modern scientists have attempted to reconstruct its mystery, blending chemistry with conjecture. Some believe Greek fire was a petroleum-based compound, thickened with resins and quicklime to ignite on contact with water. Others propose mixtures of naphtha, sulfur and saltpeter, ingredients known in the ancient world but incapable of fully explaining its persistence. The flames were said to resist sand, water, even wine, and only vinegar or urine could weaken their grasp. Such descriptions suggest not a single formula, but a mastery of chemistry centuries ahead of its time. Yet the deeper mystery lies not in what Greek fire was made of, but in how it was controlled. Byzantine engineers constructed pressurized siphons, handheld tubes, and sealed containers known as chirosiphons, a level of precision few medieval powers could match. The empire treated it as a divine weapon, stored in guarded arsenals and entrusted only to sworn specialists. Documents reveal that those who betrayed its secret faced torture or execution, and workshops producing it were hidden within Constantinople's fortified walls. In this secrecy, Greek fire transcended warfare. It became a symbol of divine favour, a flame believed to burn with the sanction of heaven. The ruins of Constantinople still whisper of that devotion to secrecy. Archaeologists have uncovered charred amphorae and corroded bronze nozzles near what was once the imperial arsenal, though none reveal the full design. The writings of Anna Komnene, daughter of Emperor Alexios I, describe the weapon as a fire sent by God, noting that its ignition came from a device made by artifice of man. Her words reveal a tension between belief and knowledge, the struggle to explain a creation that seemed to border on the miraculous. Even in the twilight of the empire, the secret remained unbroken, as if protected not by loyalty alone, but by the weight of its own danger. Elsewhere in Europe, the legend of Greek fire took on a life of its own. Crusaders, Venetians and Saracens all claimed to have captured samples or recreated its blaze, yet none succeeded in reproducing its terrifying precision. The closest imitation, a crude incendiary using oil and pitch, lacked the unpredictable brilliance that had once decided the fate of empires. When the Ottomans finally conquered Constantinople, the true formula was already gone, buried beneath centuries of siege and silence. What remained was not the weapon itself, but the myth of its creation, a memory of fire that water could not quell. In recent years, chemists and historians have turned once more to the fragments. Byzantine accounts reference naphtha imported from the Caucasus, suggesting the empire exploited the natural oil fields around the Black Sea. The addition of quicklime could explain the fire's violent reaction to water, producing both heat and ignition. Yet no single reconstruction has captured its full behaviour, leading some to believe that Greek fire was more than chemistry. It was engineering, alchemy and control combined. Perhaps the Byzantines used pressurized bronze chambers to atomize the mixture, creating a primitive form of flame projection unknown elsewhere in antiquity. The mystery deepens when one considers the weapon's survival through centuries of warfare. Greek fire remained effective from the 7th to the 12th century, an era that saw empires rise and fall, technologies flourish and vanish. That endurance implies continuous refinement, knowledge passed through an unbroken line of craftsmen sworn to secrecy. Their silence may have been the empire's last defense, for when the final masters died, the flame that had once guarded Constantinople was extinguished not by conquest, but by time. Even now, faint traces of its existence linger in laboratories and legends alike. Researchers who test reconstructions note an eerie similarity, a thick, hissing flame that resists water and crawls across surfaces with unnatural persistence. Yet every experiment ends the same way, incomplete, uncertain, shadowed by something that cannot be measured. Perhaps the secret of Greek fire is not meant to be rediscovered, for what it consumed was not only wood and flesh, but the boundary between science and myth. Far beyond the reach of time's quiet erosion, the secret of Greek fire still burns, unseen, unspoken, and impossibly alive. Egyptian blue. After millennia, the walls of Egypt's tombs still hold their colour, and with it a secret that once belonged to light itself. The shade is neither the deep azure of lapis nor the fleeting tone of dye. It is colder, steadier, and curiously alive. When torches gutter in the tomb's still air, it does not dim. When centuries of darkness settle over it, it does not yield. Among pigments that vanish, crack, and turn to dust, this one endures as if time itself were powerless against its design. For the Egyptians, blue was not merely a colour but a declaration of the divine. It symbolised the heavens, the Nile, and the pulse of creation that bound gods and mortals together. To paint the skin of Ammon or the hair of Isis in blue was to invoke eternity. To decorate tombs with its hue was to promise that the soul would not fade as the body did. Yet in this devotion lay something more than artistry. It was a controlled encounter with transformation, with heat, with chemistry so precise that even now its perfection unsettles modern science. Modern analysis would reveal that this eternal hue was no accident of mineral or myth. Egyptian blue, or calcium copper silicate, was the world's first synthetic pigment, the earliest evidence of human chemistry. Its creation required temperatures exceeding 850 degrees Celsius, demanding furnaces that could sustain intense uniform heat. The recipe was exacting, a fusion of quartz sand, limestone, copper and natron, ground and fired until matter itself changed its state. What emerged was not simply colour, but a crystalline compound that captured and reflected the visible spectrum in a way nature rarely allowed. To create it, the ancient craftsmen achieved what modern chemistry once thought impossible. They manipulated temperature with precision, controlling the transition from mineral to glass without the aid of thermometers or recorded formulas. The furnaces that produced Egyptian blue were likely fueled by acacia and date palm wood, stoked through night and day by artisans who could judge the reaction of flame by its tone and hue. Every batch was the product of both calculation and instinct, a balance between human observation and elemental power that borders on alchemy. Fragments of this pigment have been found scattered across the empire's ruins, still radiant after millennia. In Amarna, Thebes and Saqqara, archaeologists have uncovered shards of statues, painted tiles, and hieroglyphs whose blue glows faintly under light even today. Chemical degradation has not dulled its saturation, and in the right conditions, the pigment emits a faint, otherworldly luminescence. Unlike organic dyes that dissolve with exposure, Egyptian blue remains steadfast, impervious to moisture, temperature, or decay. In its endurance, it carries the strange impression of intent, as if its makers had foreseen its need to survive the world that would forget them. In recent decades, microscopic studies of pigment fragments taken from statues and temple walls have revealed astonishing consistency across centuries of manufacture. Samples from Giza, Luxor and Abydos show nearly identical particle structures, suggesting that Egyptian artisans followed standardized methods long before the concept of industrial production existed. The uniformity implies a network of specialized workshops, perhaps overseen by priestly engineers who guarded the formula as sacred knowledge. This organization of color-making hints at a hidden order within Egyptian science, a system of precision, secrecy and continuity that modern researchers are only beginning to recognize. It was only in the modern era, beneath the lens of spectroscopy, that Egyptian blue revealed its second secret. When exposed to infrared light, it glows again, not in visible color, but in wavelengths beyond human sight. That invisible radiance captured by modern instruments proves that the pigment continues to emit energy thousands of years after its creation. This discovery has transformed it from an archaeological curiosity into a subject of advanced research, inspiring technologies in biomedical imaging telecommunications, and even security tagging. What the ancients made for temples and tombs now informs the tools of the digital age. Even in its rediscovery, the pigment seems to resist full understanding. Scientists debate whether its creators were aware of its infrared emission, whether it was a deliberate byproduct or an unknown miracle of composition. Yet, to dismiss their understanding would be to underestimate a civilization whose mathematics guided the stars and whose architecture defied erosion. In every sense, Egyptian blue behaves as if born from deliberate mastery, not chance. It embodies a language of chemistry long forgotten, written in the syntax of colour and light. What Egyptian blue offers is not only a story of colour, but of continuity, the endurance of knowledge through silence. It is a reminder that not all brilliance fades, that some technologies vanish not through failure but through secrecy, through reverence, or through the quiet forgetting that follows collapse. The pigment remains as the last trace of a mind that once saw matter differently, that understood heat, mineral and transformation as expressions of divine order. In its glow, ancient Egypt speaks across millennia, not in words, but in the steady light of its own invention. And perhaps, hidden within that glow invisible to the eye, the ancients left a message we have yet to read. Chinese earthquake detector. It began with a tremor no one could hear. Deep beneath the plains of ancient China, the earth shifted in silence, pressing against itself with the weight of unseen power. In an age when the heavens were believed to mirror the pulse of the ground, such movements were more than natural. They were messages, as if the world itself was trying to speak. In Luoyang, a bronze urn once stood against the wall of an imperial hall. Around its body were 8 dragons, each holding a small bronze ball in its mouth, and beneath them 8 toads waited with open jaws. The arrangement seemed ceremonial, perhaps even decorative to the untrained eye, yet its purpose was far from symbolic. The device was said to feel the stirrings of the earth long before any tremor reached human feet. When the first ball dropped, there had been no shaking in the city. The court remained silent, unsure of what they had witnessed, only a single metallic note ringing through the hall as the sphere landed in the mouth of a toad. Days later, a messenger arrived from the west, reporting devastation in distant provinces. The emperor, astonished, realized that the falling ball had marked the direction of the quake before word could travel. What had seemed like a curious object was now regarded as a marvel of divine insight, a bronze vessel that could sense the language of the world below. Zhang Heng had always studied the patterns that bound heaven and earth. Known for his mastery of astronomy and mathematics, he saw the cosmos not as separate from the human realm but as its reflection. His inventions were built from that belief, a harmony between order and chaos, calculation and faith. The earthquake detector, or Hufeng Didong Yi, was not merely an instrument of measurement. It was a symbol of unity between the celestial and the terrestrial, an embodiment of how precision could coexist with reverence. What moved within the bronze shell has never been seen. No surviving text reveals its exact design, though many have tried to imagine it. Some believe it contained a system of pendulums that swayed with seismic vibrations. Others suggest channels filled with mercury, shifting with invisible motion to trigger the release of a single ball. Its inner workings remain hidden, an ingenious secret sealed in lost metal. What endures is the fact that it worked, that this device, crafted in the 2nd century, could detect tremors hundreds of miles away with astonishing accuracy. After Zhang Heng's death, the device vanished from record. No replica survived the passage of dynasties, and no illustration was preserved to guide later generations. Knowledge, once so carefully guarded, slipped into silence. Centuries later, chroniclers mention Zhang Heng's invention only in fragments, often with tones of disbelief, as if it belonged to myth. The instrument that had listened to the ground's voice was lost, as though it had returned to the earth it once understood. Nearly 2 millennia later, the silence was broken again. In the 20th century, Chinese historians and engineers attempted to reconstruct Zhang Heng's seismoscope based on ancient descriptions. Using bronze and traditional casting techniques, they built replicas that mirrored the original's form: 8 dragons, 8 toads, and a hollow core of intricate weight. When tested, these replicas reacted to distant seismic activity with remarkable precision. One model at the Chinese Academy of Sciences recorded movements that instruments could barely trace, confirming what history had long whispered, that Zhang Heng's creation had been a true instrument, not a legend. For the Han, earthquakes were not geological, they were celestial messages. The empire's stability was thought to reflect cosmic order, and when the ground quaked, it was seen as a moral warning to the emperor. Records show that after certain tremors, emperors performed public acts of repentance or reformation, believing that an imbalance in rule had disturbed the harmony of the world. In that sense, the Hufeng Didong Yi was more than a tool of science, it was an instrument of conscience, a way for rulers to sense divine disapproval before it arrived in ruin. Scholars today still debate how Zhang Heng achieved such sensitivity with the limited technology of his age. Some point to his deep study of mechanical systems used in ancient armillary spheres, complex celestial globes that could mirror planetary movement through careful gearing. Others suggest that he may have observed how ripples spread through water, or how pressure shifted in confined vessels. Whatever the truth, his invention stood as an early marriage between physics and philosophy, reflecting a worldview that saw no divide between science and spirit. Modern seismology owes its roots to devices like Zhang Heng's, though few acknowledge it. The principles behind his seismoscope, motion, suspension, directional indication, reappear in every modern sensor transformed by electricity and computation. Yet the bronze urn of Luoyang carries something those machines do not, a stillness that listens, not measures. It reminds the world that detection began not with progress, but with wonder, with one man's faith that the Earth was capable of speech. In 2005, a Chinese research team constructed a full-scale replica that accurately detected simulated tremors from hundreds of kilometers away. Some reports claimed it could distinguish directional vibration with near-perfect precision, while others found inconsistencies under controlled conditions. The truth, as with much of Zhang Heng's legacy, remains suspended between evidence and awe. What cannot be denied is that an ancient mind, guided by observation and belief, built something so advanced that even modern science hesitated to call it primitive. Maybe that is what lingers most, the quiet persistence of an idea born from stillness, the notion that the world speaks long before it moves, and that once, in a time of emperors and scholars, someone found a way to listen. And if the Earth could once speak through bronze, perhaps it is still speaking now, waiting for someone to remember how to hear. Baghdad Battery. Under the cold light of a museum display, the small clay vessel looks harmless. Its cracked surface bears the quiet erosion of centuries, the kind of artifact that rarely stirs debate. Yet behind the glass, the label carries an unease that no ordinary pottery inspires. Possible ancient galvanic cell. The phrase is careful, uncertain, as though even the museum itself isn't ready to claim what the jar might truly be. Scholars have studied it for decades, not because it fits neatly into the story of invention, but because it doesn't. Decades earlier, it was pulled from the soil near Hujat Rabu, just outside Baghdad. The year was 1938, and the excavation, led by Wilhelm Koenig, revealed what appeared to be a simple collection of Parthian-era jars. But one vessel caught Koenig's attention, a small, rough cylinder sealed with bitumen and containing a rolled sheet of copper surrounding a corroded iron rod. It was too deliberate, too precise to be accidental. Koenig, an Austrian archaeologist and museum curator, suggested something few were willing to imagine, that it was a form of ancient battery. The object's construction defied simple explanation. The jar stood roughly 15 centimeters tall, with the copper cylinder carefully fitted inside and insulated by the bitumen plug. The design was oddly familiar to modern eyes, resembling the basic layout of an electrical cell. When analysed, residues of acidic compounds were found inside substances that could, in theory, generate a weak electrical current when the copper and iron were connected through an electrolyte. It was the kind of arrangement that would not reappear in known science until nearly 2 millennia later. When scientists filled replicas with vinegar and copper sulfate, the impossible happened. A small but measurable voltage flickered through their instruments, barely half a volt but unmistakable. For a moment, the past seemed to bridge a gap of centuries, whispering of knowledge lost and rediscovered. The tests were repeated under controlled conditions, and each time the outcome persisted. the jar could produce electricity. Whether by design or by chance, it was capable of holding a charge. Yet not all agreed that it was a battery. Some argued that the device might have been used for electroplating, a technique for coating objects in gold or silver. Others dismissed the idea entirely, claiming it was simply a storage jar for sacred scrolls or papyrus. The absence of clear textual evidence left every explanation standing on uneven ground. Archaeologists cautioned that even successful reconstructions didn't prove original intent. After all, coincidence could mimic design. But that argument too carried its own unease, because coincidence seemed an unlikely author of such precision. To understand how such a device could exist, one must return to the Parthian world. Between the first centuries BCE and CE, their empire bridged east and west, blending the technologies of Persia, Mesopotamia, and Greece. Skilled in metallurgy, glassmaking, and hydraulic engineering, they were not strangers to experimentation. Copper and iron were abundant. Bitumen was used in sealing and insulation. In that context, the idea of a chemical reaction occurring within a sealed vessel no longer felt implausible. What remains uncertain is purpose. What ancient hands intended the charge to do? After its discovery, the artifact fell into obscurity as quickly as it had emerged. Koenig's papers were stored in archives and went largely unread during the war years that followed. By the time researchers revisited his findings, the original context of the excavation had faded. Replicas were built and displayed across museums, each claiming descent from the same mysterious jar. Yet without more examples, no conclusion could take root. The single vessel from Kujut Rabu stood alone, a relic whose significance evaporated with time's silence. In recent years, engineers and historians have continued to revisit its mystery. Some have experimented with a series of similar jars, connecting them as primitive batteries capable of generating enough voltage to electroplate small objects. Others have searched nearby excavation sites for traces of metallic residue or instruments that might confirm electrical application. A few findings suggest that gilded artifacts from the same region show unusual surface characteristics, microscopic smoothness consistent with electrochemical plating, but the evidence remains inconclusive. Modern science has since expanded the discussion. A 2019 analysis by materials specialists re-examined residues from the vessel's interior, proposing that natural acids from wine or fermented fruit could indeed act as electrolytes. The theory rekindled debate not only about the Baghdad battery itself, but about the broader notion that ancient engineers may have stumbled upon principles of electrochemistry through craft rather than theory. If so, they may have understood the behaviour of materials more intuitively than the structured science that came much later. In this way, the Baghdad battery mirrors a recurring pattern in ancient innovation: moments of brilliance that appear abruptly, function perfectly, and then vanish without lineage. Like the Antikythera mechanism or Roman concrete, it stands as a solitary witness to knowledge that arose outside the timeline of progress. It challenges the assumption that discovery follows a straight path and forces historians to confront a disquieting thought. Perhaps some truths are found too early, only to disappear until the world is ready for them. The jar now rests in the National Museum of Iraq, displayed behind reinforced glass. Its copper gleams faintly through the dust of age, its iron rod darkened by corrosion. Visitors pass without much notice, unaware that within its hollow frame lies a question that has never been resolved. The small vessel endures as both evidence and enigma, its silence as charged as any current it may once have carried. And time sealed the vessel, but not the question of what once lived inside it. The Lycurgus Cup. At a feast in late 4th century Rome, the chalice arrived as triumph incarnate. It gleamed beneath torchlight, resting on the polished marble table among dishes of silver and bowls of fruit. Senators, courtiers, and generals lifted their eyes to it as if it were alive. The host, one of the empire's last great patrons of luxury, held the vessel high, and the glass shifted in colour. A soft green in the glow of the lamps, a deep blood red when caught by firelight. No one present could have known that the cup would outlive the empire itself, or that its strange power over light would one day puzzle scientists as much as its beauty once awed Rome's elite. The outer cage of the vessel depicts the fate of King Lycurgus, the Thracian ruler who defied Dionysus and was punished for his defiance. Twisting vines coil around the king's limbs as he's consumed by the god's wrath, a myth cast into glass with haunting precision. The artisans had trapped a story in a shell of shimmering material, fusing art and warning into a single object. To the Romans, such a piece was not merely decoration, but a form of moral theatre, the dangers of hubris sealed in light and wine. It was said that even in stillness, the figures appeared to shift, as if the vines themselves continued their slow, divine revenge. In daylight, the cup appears a tranquil jade green, but when illuminated from within, it turns the deep red of spilled wine. The transformation is so abrupt, so otherworldly, that even now it feels less like a trick of science and more like a ritual. Modern observers have compared it to a living thing, glass that breathes, that alters its face with mood and light. In the ancient world, no other artifact demonstrated such behaviour. For centuries, the secret of its transformation was forgotten, lost with the fall of the empire and the silence of its workshops. The cup survived by chance, passing through ruins and private collections until it was quietly placed in the British Museum, where it rests under controlled light, forever between green and red. Microscopes would later reveal particles of gold and silver, suspended within the glass like dust in the air, each one smaller than a virus. The artisans, working without any concept of nanotechnology, had achieved what modern science would rediscover only in the 20th century. The metal particles scattered and absorbed light with remarkable precision, altering their colour depending on the direction of illumination. This phenomenon, known today as dichroism, lay hidden in the cup for over a millennium, yet the method of embedding those nanoparticles, balancing their ratios, and achieving uniform dispersion in molten glass remains largely unknown. The Lycurgus cup became not just an artwork, but a scientific anomaly, evidence that the ancients had once grasped principles of material behaviour far ahead of their time. No ancient manual survives to explain how the artisans achieved this effect. The Romans recorded recipes for coloured glass, yet none mention metallic dust or the fusion of precious metals into molten silica. Scholars suspect the process was guarded by a few glassmakers working in imperial workshops, specialists whose knowledge passed through apprenticeship, never through text. When their lineages ended, so too did the craft. What remains is an artifact that seems to contradict the age it came from, standing as proof that something extraordinary once existed, then simply vanished. The silence surrounding it feels deliberate, as if the method was never meant to be shared beyond the palace walls. The cup likely emerged from workshops that catered only to emperors and their courts, those who sought not utility but immortality through art. Such places operated at the margins of secrecy, guarded by trade restrictions and imperial decrees. Their furnaces produced goblets for ceremonies, vessels for relics, and lamps whose light was said to resemble dawn. But when the empire fractured, its supply of metals, craftsmen, and wealth collapsed. Workshops were abandoned, apprentices scattered, and the art of Roman glassmaking declined into memory. The Lycurgus cup became a relic not only of myth, but of a lost technological world, its survival a rare and accidental mercy. In modern laboratories, scientists and artists have tried to reproduce the Lycurgus effect using lasers, nanoparticles, and 3D printing. Some succeeded in mimicking its optical shift, yet none could recreate its particular balance of colour and clarity, the exact hue that drifts between emerald and rose, like sunlight through stained water. The more technology advances, the more the original seems unattainable. What was once the product of intuition and guarded experiment now demands the precision of modern physics. And still the cup holds something that resists replication, a feeling that its colour change belongs less to chemistry than to consciousness itself, as if the vessel reacts not only to light but to the gaze that falls upon it. This single surviving cup stands at the crossroads of art, science, and loss. It embodies the paradox of ancient mastery, knowledge refined beyond its own survival, brilliance buried beneath collapse. Every facet of it, from the myth it portrays to the metal hidden within, reflects a civilization's pursuit of permanence against the inevitability of decay. It is both artifact and apparition, preserved yet unknowable, shining in two colours like a message meant for those who came too late to understand. In the faint blush of ruby and the quiet shimmer of green, the cup still guards the light that no hand can fully command. The fireproof cloth of Herculaneum. When the city of Herculaneum was consumed by fire in 79 CE, nearly everything that once belonged to its people should have vanished in the furnace of Vesuvius. The volcanic surge that buried the town reached temperatures capable of incinerating bone and bronze alike, yet among the brittle relics unearthed centuries later was something that should not have survived. In a villa overlooking the ancient shoreline, excavators discovered a fragment of woven material that had resisted destruction. It had not merely endured the flames, it seemed to have defied them. Early accounts described the find with quiet astonishment. The archaeologists who first examined it in the 19th century believed the fabric was a linen-like cloth, carbonized but strangely intact. What caught their attention was that when exposed to flame once more, the relic refused to burn. Instead, it darkened, hardened slightly, and cooled without turning to ash. The discovery challenged every known expectation of what could endure in such conditions. In a city reduced to charcoal and bone, this cloth had become an anomaly in the record of destruction. The ancient writers had hinted at substances that could resist flame. Pliny the Elder mentioned a mineral wool drawn from the earth near the island of Cyprus, so fine it could be spun and woven like fabric. The Romans, he wrote, cleaned it in fire rather than water. Later historians recognized this as asbestos, the heat-resistant mineral known to ancient builders and priests. If the cloth found in Herculaneum was indeed asbestos-based, it would fit a lineage of forgotten Roman experimentation, a material prized for purity in sacred rituals and shrouds. Yet the mystery was not so simple. The sample's texture suggested a blend, something more refined than raw asbestos or linen alone. As studies progressed, researchers found that the fabric seemed to consist of interlaced fibers coated in a mineral layer, possibly calcium or silica, which formed a protective shell during combustion. Such a composition would have been far beyond the capability of ordinary Roman weavers. This hinted at specialized workshops, perhaps attached to temples or aristocratic estates, where artisans manipulated natural minerals into woven composites. No written record of such work survives, but Pliny's accounts and fragments from later writers describe a fascination among Roman scholars with materials that imitated the permanence of stone. It was not immortality they sought, but resistance, a way to preserve sacred forms against decay. The question of its purpose remains unresolved. Some theorized the cloth might have been ceremonial, used to wrap offerings placed near eternal flames in temples of Vesta or Vulcan. Others suggested it served in practical applications, lining cooking vessels or shielding valuable goods from heat. The presence of the fragment in Herculaneum complicates the matter. This was a coastal resort, a place of leisure, not worship. Perhaps the villa's owner was among those wealthy Romans who collected rare curiosities, proof of the empire's ingenuity, and kept them for private display. If so, the cloth's survival was not divine intervention but coincidence, a relic of wealth trapped in volcanic silence. Rather than offering clarity, modern examination has only renewed the enigma. Small samples taken for testing revealed structural properties remarkably similar to early industrial asbestos cloths, produced in the 19th century. Its fibers, under magnification, appeared crystalline and layered, each strand forming a lattice that repelled flame. Some researchers even proposed that the ancient artisans used an early form of heat treatment to strengthen the fibers, suggesting a primitive understanding of thermal chemistry. Such precision seemed implausible for its time, yet the Romans were known for material mastery, their hydraulic cement, their alloys, their pigments that never faded. Perhaps this fireproof cloth was one more achievement lost to time. Despite the intrigue, the sample itself has almost vanished through study. Each century's testing consumed fragments until only traces remain in museum collections. Early collectors handled the material carelessly, unaware of its significance, and portions were destroyed by well-meaning experiments. The original context of its discovery has also been lost to excavation errors. No one can say for certain which layer of ash preserved it, or whether it was found alone or among other woven goods. All that endures are a few lines in excavation notes and the testimony of those who witnessed its defiance of flame. There are echoes of similar tales from antiquity, reports of fabrics that could be thrown into fire without harm, or veils that purified themselves in flame. Greek historians told of the living cloth of the temple at Athens, renewed each year but never burned. These accounts were dismissed for centuries as myth, yet the fragment at Herculaneum forces a reconsideration. If one such material truly existed, then perhaps ancient craftsmen had learned to combine mineral and organic matter in ways that have not been replicated since. Their formulas, once common knowledge within a closed guild, may have perished with the cities that nurtured them. The story of the fireproof cloth mirrors the paradox of Herculaneum itself, a place preserved through destruction, where annihilation became a form of preservation. The material's endurance serves as a small defiance against time's authority, its surface still faintly textured with the weave of human hands. Those hands belong to workers who likely never saw the mountain's final fury, and yet their craft endured long after their names turned to dust. The fabric, found amid the charred remnants of civilization, becomes not just an artifact, but a question. How did a culture so advanced in material science allow such knowledge to disappear? To this day, scientists attempting to replicate the cloth's properties have only approximated its resistance. The precise balance of mineral coating and fibre remains elusive. What lingers instead is the symbolism of its survival, a fragment that turned disaster into proof of ingenuity. In a world where stone buildings melted and metal fused, one small piece of fabric refused to surrender its form. In a chamber long silenced by ash, the cloth remains, defying both combustion and comprehension. Roman flexible glass. Not in the din of labour, but in the hush of a court, the story begins. A craftsman presenting a vessel the world was never meant to see unbroken. The legend tells of a man who appeared before Tiberius Caesar, holding what seemed to be an ordinary glass cup. Yet within that object shimmered something strange, an unyielding quality that defied the brittle nature of all known glass. No one could say where the man had come from, or how long he'd worked to perfect the substance. What mattered was the moment he stepped into the marble hall of imperial judgment, holding a creation that would soon test the boundaries between invention and fear. When the craftsman hurled his creation to the marble floor, the sound that followed was not the shatter of glass, but the dull ring of resilience. Those who watched expected fragments to scatter across the tiles, yet the cup only dented slightly, folding inward like soft metal. Calmly, the man lifted it and produced a small hammer, tapping the surface until it resumed its original shape. Petronius, in his Satyricon, framed the scene with a satirical eye, perhaps mocking the excess of emperors and the vanity of invention. But the image he painted lingered in Roman memory. Pliny the Elder, too, mentioned a craftsman who had discovered a way to make glass unbreakable, only for his discovery to vanish. And Dio Cassius, decades later, recalled the same encounter as rumour rather than fact, yet with details too consistent to ignore. The emperor, astonished but calculating, demanded whether anyone else knew of this invention. The craftsman swore that no one did, that he alone possessed the secret of its making. For a moment the emperor said nothing, perhaps weighing the worth of what he had just seen against the peril it carried. According to the tale, Tiberius then ordered the man executed, fearing that such a material, if made known, would devalue gold and silver and overturn the delicate order of wealth itself. The story's violence feels allegorical, yet it mirrors the logic of empire, that certain discoveries are too disruptive to survive. In Rome, progress was permitted only when it served the hierarchy that governed it. Petronius wrote of it as satire, Dio as rumour, Pliny as faint recollection, and yet their accounts echo one another with unsettling precision. Each positioned the event differently, but none dismissed it entirely. Petronius used it to mock imperial vanity, while Pliny approached it with the cautious tone of a natural historian, cataloguing curiosities that might or might not be real. Dio Cassius, writing later, recounted it as hearsay that refused to die. Such repetition across generations gave the story a strange durability. It did not belong wholly to myth or history, but to that uncertain ground between, where forgotten truths often take root. Modern researchers have wondered whether the story hides an early form of malleable glass, a lost art of controlled annealing or metal-glass fusion. Some scientists have speculated that ancient artisans might have stumbled upon a technique similar to what modern materials science now calls metallic glass, a substance created when molten alloys are cooled rapidly, preventing the crystalline structure that makes metals rigid. Roman craftsmen, working with furnaces capable of remarkable precision, could conceivably have experimented with mixtures of glass and metal oxides, producing a hybrid that flexed without fracturing. Others suggest that vitrum flexile, as it was later called, could have been a misinterpretation, a poetic exaggeration of a glass unusually resistant to breakage. Yet the persistence of the legend implies something tangible that once existed behind it, however faintly remembered. Rome's artisans pursued permanence as though it were conquest itself. They created concrete that hardened underwater, alloys that shimmered like gold, and glassware tinted with rare minerals from distant provinces. The empire's wealth was not only in its armies or its territories, but in its materials, its ability to transform sand, ash, and ore into symbols of eternity. Within this culture of mastery, a form of unbreakable glass would have represented more than a novelty. It would have been a defiance of nature, a step toward immortality through craft. To imagine that such an invention was real is to glimpse the ambition that pulsed beneath Rome's marble facades, an obsession not with beauty alone but with dominion over the physical world. To a ruler, innovation could be as dangerous as rebellion. The empire's economy depended on the scarcity of its luxuries. Gold and silver were not merely metals but instruments of power. A glass that could not break, that could replace or rival precious metals, threatened the very foundations of Roman wealth. It is telling that the emperor's alleged reaction was not curiosity but fear that progress could dissolve privilege. In this way, the tale of the flexible glass becomes less a fable of invention than a commentary on authority itself, revealing how knowledge was often suppressed not for its failure, but for its potential to succeed too well. Centuries later, alchemists and natural philosophers would speak again of glass that bent and did not break. Medieval manuscripts mention experiments with softened glass, and during the Renaissance, Venetian glassmakers whispered of secret formulas that produced materials with strange resilience. Even in the 17th century, English and French experimenters claimed to have rediscovered ductile glass, though none could reproduce it consistently. Each rediscovery seemed to echo the Roman legend, as though the memory of the craftsman's lost art had never fully disappeared, only receded into myth, waiting for hands bold enough to restore it. If it ever existed, it vanished not by chance but by command. The story of the craftsman and his unbreakable vessel stands as a symbol of how easily invention can be silenced by power. Whether a parable or a buried truth, it speaks of the fragile balance between human ingenuity and the fear that governs it. In the ruins of Rome, shards of ancient glass still glint beneath the soil, delicate, translucent, unchanged by centuries, as if mocking the silence that followed that fateful demonstration. Between the light of creation and the quiet weight of empire, the secret of unbreakable glass was lost to time. Heron's steam engine, Aeolipile. Long before the first industrial engines churned in Europe, a small brass sphere once rotated silently above a cauldron of boiling water, powered by nothing but steam. Known as the Aeolipile, this device transformed vapour into motion, a principle that would not be widely understood for more than 1,000 years. Its hollow arms expelled jets of gas with precision, causing the sphere to turn on its pivot as though guided by unseen hands. To the observer, the motion seemed magical, a fleeting glimpse of forces harnessed long before their time, and yet it existed purely as an experiment in motion and pressure, a demonstration of ingenuity in an age that would not fully grasp its potential. Heron, working in the libraries and workshops of Alexandria, distilled the principles of motion and pressure into bronze and steam. In a city renowned for its collection of scrolls and instruments, he studied not only mathematics and mechanics, but the curious behaviours of air and water under constraint. His treatises reveal an understanding of pneumatics and hydraulics, capable of producing doors that swung open through fire, fountains that mimicked living creatures, and other devices that seemed almost magical in their ingenuity. The Aeolipile was no mere novelty. It represented an abstract comprehension of forces that would not be formalized again until the age of industrialization. Alexandria itself, a nexus of trade and intellect, offered Heron a rare convergence of materials, patrons, and knowledge that allowed such an invention to emerge, though its broader implications remained unnoticed at the time. Two hollow, opposing arms extended from the sphere, angled precisely so that as steam escaped, the resulting jets propelled the device into steady rotation. The engineering was deceptively simple in form but profoundly sophisticated in principle. The vessel was balanced on a pivot, its bronze body carefully shaped to resist friction and maximize the effect of the vapor. Water boiled below, producing a steady stream of gas that flowed through pipes into the sphere, demonstrating an intuitive grasp of pressure, energy conversion, and rotational dynamics. Even the materials used were chosen with care, bronze being both durable and capable of withstanding repeated heating without deforming. The Aeolipile thus became a tangible lesson in the invisible forces that surround the ancient craftsman, turning theory into continuous spinning reality. Writers and scholars centuries later marvelled at the spinning orb, though few understood its purpose beyond the curiosity it inspired. Descriptions in texts by engineers and philosophers suggest it was admired for its elegance and novelty, not as a tool of labour or warfare. Surviving diagrams show a careful attention to the flow of steam and the pivoting mount, yet no instructions for practical application were preserved. It existed within a culture that celebrated spectacle and ingenuity, but lacked the industrial context to exploit its potential. In this sense, the Aeolipile is emblematic of a broader pattern in ancient invention, where mechanisms of extraordinary sophistication appear briefly before fading into silence, their genius glimpsed only by those willing to examine the fragments that remain. Despite its ingenuity, the Aeolipile vanished from practical use, leaving only fragments of text and brass to hint at its existence. The knowledge of Heron's work did not die with him, but it did not flourish, confined to manuscripts that survived precariously through centuries of upheaval. It is unclear whether the device was ever copied for any functional purpose, or whether it remained a demonstration piece, admired for curiosity rather than productivity. Unlike water wheels or aqueducts, which found lasting applications, the spinning sphere seemed to offer no immediate advantage to the societies that followed. Its disappearance underscores a silent mystery, how such understanding of thermodynamics, encoded in simple bronze and steam, could vanish so completely from the human record. In laboratories centuries removed from its first spark, Heron's device would resurface, though the brass that once powered it had grown cold. Engineers experimenting with steam in Italy and England were rediscovering unknowingly what had already been achieved in Alexandria. The Aeolipile had offered a blueprint for motion without muscle, a fundamental concept of mechanical energy, yet it remained unrecognized for over a millennium. Scholars have speculated on the lost potential of ancient engineering, imagining workshops where Heron's sphere might have inspired machines of industry centuries before they were realized. The faint echo of its invention survived in texts, but the practical knowledge faded into obscurity, leaving only a conceptual shadow for those who would later pursue steam power in earnest. Modern engineers marvel at the Aeolipile not only for its mechanics, but for the subtle understanding of forces encoded in its motion. Tests of replicas demonstrate that it operates with remarkable efficiency given the simplicity of its construction. The device illustrates the universality of natural laws, bridging the gap between antiquity and modern scientific thought, and it forces reflection on the fleeting nature of knowledge and innovation. Heron's insight into the conversion of heat into kinetic energy was not theoretical alone. It was proven in brass and vapor, a living demonstration of forces that would take centuries to harness fully. In this context, the Aeolipile represents both a lost chapter of human ingenuity and a haunting reminder of how ideas can drift into silence. No workshop today reproduces the Aeolipile as Heron imagined it, and yet the sphere spins still in the mind's eye, a whisper of motion suspended between what was known and what has been forgotten. Shadows of steam and bronze linger in the corners of ancient laboratories long vanished, hinting at the knowledge that once flowed freely through the hands of the curious. Each rotation, imagined or real, carries a faint echo of discovery that history allowed to slip quietly into silence. The brass orb turns endlessly in imagination, and somewhere in its ghostly rotation lies the question no engineer has yet answered. Nabatean water systems of Petra. Through carved stone channels and vaulted cisterns, water was guided with such precision that the survival of Petra itself seemed almost impossible. In a city hewn from rose-coloured cliffs, where rainfall was sporadic and the desert heat relentless, the Nabateans turned scarcity into an opportunity for ingenuity. Every drop was captured, diverted and stored, a silent testament to minds that understood both the unforgiving environment and the delicate calculus of survival. The canals and reservoirs hidden from casual view carried life invisibly through the city, sustaining traders, artisans, and pilgrims alike while remaining largely imperceptible to outsiders who marveled only at the towering facades and winding canyons. The Nabateans, a desert people renowned for their skill in trade and adaptation, transformed rock into a labyrinth of water harvesting structures. They carved cisterns into cliff faces, hewed channels into bedrock, and constructed reservoirs lined to retain every precious drop of rain or runoff. Archaeological evidence suggests they developed terraced collection systems and subtle gradients that allowed water to flow reliably without pumps, relying solely on gravity and precise calculation. Their ingenuity extended beyond mere survival. It was an intimate knowledge of hydraulics and stonework, engineered to operate unseen yet flawlessly throughout the city. Every carved chamber and narrow ledge carried water with meticulous design, each slope and joint calculated to maintain flow while minimizing evaporation. Vaulted cisterns could store thousands of litres, their interiors coated to prevent leakage, and channels ran along cliff faces and through rock-cut conduits, connecting distant reservoirs. Some conduits are only wide enough for a single person to inspect, suggesting that maintenance requires both skill and courage. The subtle integration of these structures into the natural stone made the system nearly invisible, protecting water from theft in the desert sun, and leaving behind a silent network whose full extent even modern surveys struggle to map. Ingenious dams and settling basins intercepted silt and debris, ensuring that water flowed clean through the labyrinthine conduits. The Nabateans carved barriers directly into the rock to slow the pace of rushing runoff, directing heavier sediment into separate pits while allowing clear water to continue towards cisterns and terraces. Some channels ran through hidden tunnels behind cliff faces, keeping the liquid cool and reducing evaporation under the desert sun. In certain reservoirs, layers of sand and gravel acted as natural filters, purifying captured rainwater before it reached homes, gardens, and fountains. This combination of subtle engineering, practical observation, and adaptation to a harsh climate demonstrates a mastery of hydraulics that would not be seen again for centuries, leaving a faint but enduring testament to ingenuity now lost with the city. During the occasional desert storms, torrents that might have swept away buildings were intercepted by channels that funneled water into holding cisterns and terraces. Rainfall that could have been destructive instead became a source of life, captured and stored for times of drought. Ingeniously, the Nabateans built overflow systems and settling basins, ensuring sediment did not clog vital channels. This capacity to anticipate both scarcity and abundance reveals a sophisticated understanding of hydrology that has puzzled scholars for centuries, a knowledge encoded in stone and carried in water, yet almost entirely lost with the city itself. From these reservoirs, water flowed invisibly into the city, supplying public fountains, private homes, and agricultural terraces below. Archaeological evidence shows channels reaching far beyond the central urban area, providing irrigation to gardens and sustaining livestock. Some fountains were ornamental, their design reflecting both status and the Nabateans' desire to display control over the precious liquid. Yet the movement of water remained largely hidden, a network operating in silence, ensuring that daily life continued uninterrupted, even in the harshest conditions. It is a system as elegant as it is practical, one whose techniques modern engineers can study but still cannot fully replicate. When Petra declined, the knowledge of these hydraulic marvels faded, leaving only stone channels, cisterns, and the occasional inscription as traces of lost expertise. Unlike monumental facades, which survived as symbols of artistic achievement, the practical know-how of water management vanished with the people who maintained it. Scholars debate how much was oral tradition versus written instruction, yet much of the system's sophistication appears impossible to have been preserved completely. The disappearance of such advanced engineering raises questions not only about historical continuity, but also about how knowledge, even when vital, can slip quietly into obscurity. Today, archaeologists map aqueducts, cisterns, and channels with a mixture of excavation, LiDAR imaging, and careful observation, attempting to reconstruct the logic of a system that defied the desert's demands. Measurements reveal gradients so precise that water could flow over hundreds of meters without pumps, and analysis of sediment layers provides insight into maintenance cycles and storage capacity. Even with modern technology, parts of the network remain elusive. hidden behind collapsed rock or buried beneath later constructions. Each discovery inspires awe, reminding researchers that the Nabateans combined engineering, observation and adaptation to achieve what many would have considered impossible. The remnants of these water systems still speak of a mastery that vanished alongside the city's inhabitants, leaving questions about construction methods, planning and daily operation unanswered. Though stone and channel endure, the full scope of Nabatean hydraulic expertise remains partially veiled, a puzzle scattered across canyons and terraces. Modern eyes can trace the paths and speculate on function, but the living knowledge, the hands that carved and maintained these channels, is gone, leaving only traces for imagination to reconstruct. Within Petra's twisting channels, the long-vanished currents of the Nabateans may yet hold secrets beyond the reach of modern hands. The Iron Pillar of Delhi. Rising above the crowded streets of Delhi, a single pillar of iron stands unbroken, resisting centuries of monsoon and decay. Its polished surface gleams faintly in the sun, yet it has never been coated or protected by modern methods. The sheer permanence of the structure draws immediate curiosity, a testament to an ancient skill that has withstood the forces of weather, pollution, and human interference, leaving scholars and visitors alike questioning how it could endure so flawlessly through time. In the heart of Gupta-era India, a civilization celebrated not only conquest but mastery over materials, crafting monuments that testified to both divine and earthly power. The Gupta Empire fostered a cultural environment in which science, religion, and art intertwined, encouraging metallurgical experimentation alongside temple building and urban planning. Within this context, the Iron Pillar emerges as more than a singular achievement. It embodies the intersection of engineering excellence, political authority, and spiritual symbolism, a silent declaration of permanence in a world of impermanence. Carved inscriptions hint at kings and dynasties long vanished, yet the exact date and purpose of the pillar remain subjects of debate. Sanskrit text etched into its surface honours King Chandragupta II and celebrates victories of the Gupta Empire, but it offers little insight into how such a massive column was forged, or why it was designed to resist corrosion so completely. The words themselves carry history, yet they open more questions than answers, standing as an enduring record of a civilization capable of feats that continue to confound modern observers. The inscriptions also suggest a ceremonial purpose, aligning with temple complexes and possibly marking sacred or civic spaces, intertwining metallurgy with cultural meaning. Composed of nearly pure wrought iron, the pillar's material composition astonishes metallurgists even today. The iron contains unusually high levels of phosphorus and lacks sulfur and magnesium, factors that contribute to the formation of a thin protective film preventing rust. Unlike modern steel, which requires precise temperature control and alloying, this metal was forged with ancient techniques that remain partially unknown. Each layer of the pillar's surface is a record of chemical mastery, a silent archive of knowledge lost with the hands that hammered, folded and welded it into being. Comparative studies reveal that even other large iron objects from the same period corrode rapidly, underscoring the singular sophistication of this artifact. Forged in sections and carefully assembled, the pillar rises over 7 meters, weighing more than 6 tons. Scholars speculate on the methods used to hoist and align it vertically, imagining teams of craftsmen using levers, pulleys and scaffolds of wood, yet no historical record describes the process. The precision of its alignment, combined with its structural stability, indicates a sophisticated understanding of weight distribution and metallurgy. Every element, from its base to the subtle taper of its shaft, reflects intentional design meant to endure centuries of wind, rain and time, demonstrating a technical foresight that rivals modern engineering calculations. The chemical fingerprint of the pillar hints at furnaces and techniques that modern metallurgists can only partially reconstruct, revealing an expertise lost to time. Analysts suggest that repeated heating and hammering removed impurities while layering phosphorus, producing a surface remarkably resistant to corrosion. Some studies even suggest that the ancients may have understood the effects of ambient humidity and rainwater, subtly enhancing the passive protective layer. This silent, unbroken record of knowledge is encoded in the metal itself, challenging modern science to decode principles achieved millennia ago without thermometers or chemical laboratories. The pillar is more than iron, it is a monument to devotion, engineering, and cosmic symbolism. Some historians suggest its proportions and positioning align with temple structures or celestial markers, implying a dual purpose, to honour rulers and deities while demonstrating technological mastery. Its endurance may have been a deliberate statement, an assertion of permanence in both spiritual and temporal realms. The sheer resilience of the pillar transforms it into a narrative of human ingenuity, ambition, and reverence, all encoded in metal, demanding reflection on the priorities and capabilities of a civilization now vanished. Each microscopic layer of the iron is examined, each corrosion-resistant film scrutinized, as modern scientists chase a mystery that has persisted for centuries. Studies reveal the formation of a passive layer of crystalline iron hydrogen phosphate, which acts as a natural shield against rust. Even with advanced analytical tools, the exact methods by which ancient metallurgists achieved such purity and stability remain uncertain. Each sample taken from the pillar offers new insight, yet underscores the mystery. The ancients produced a material that resists time in ways that contemporary methods struggle to replicate. Through centuries of monsoon, dust, and the expansion of Delhi around it, the pillar has endured almost untouched, as if protected by the very skill that forged it. Its surface bears tiny fissures and hammer marks, reminders of the labour and technique involved, yet none have allowed corrosion to take hold. The pillar has survived human activity, invasions, and environmental exposure, standing as a testament not only to the knowledge of its creators but also to their foresight in crafting an object designed to endure. Few artifacts in the ancient world rival its combination of size, purity, and endurance, leaving scholars to speculate about lost workshops and forgotten techniques. Comparisons with other iron objects in India and abroad reveal smaller, less pure items that succumb to rust within decades, highlighting the pillar's uniqueness. Some theorists posit that ancient furnaces were carefully controlled for temperature, slag removal, and repeated hammering, yet without surviving manuals or direct evidence, the precise methodology remains unknown. The iron pillar endures as both a practical achievement and an enduring enigma, bridging ancient knowledge and modern inquiry. Rain falls, winds sweep past, yet the iron pillar remains a silent witness to centuries of history and unanswered questions. Its presence invites awe not only for what it is, but for what it conceals, a story of human skill, chemical insight, and cultural intention that continues to challenge understanding. Every glance along its shaft, every reflection on its inscriptions and uncorroded surface, evokes the hands and minds that forged it, leaving only fragments of explanation for historians and scientists to reconstruct. Hidden within its ancient alloy, the pillar preserves a secret of craftsmanship that no modern hand has yet been able to unravel. Mithridatium. Mithridates VI, king of Pontus, lived under a shadow of suspicion, convinced that poisons lurked in every banquet and council chamber. In a world where treachery was common and rulers often felled the smallest vial of toxic substance, he became obsessed with self-preservation. His paranoia was not born of fantasy alone. Political assassinations had claimed relatives and rivals alike. And in this climate of fear, the king turned his attention to a singular ambition: to render himself immune to death by poison. The pursuit of this goal would eventually give rise to a legendary mixture known as Mithridatium, an antidote whose very existence blurred the line between science and legend. To defend himself, Mithridates subjected his body to small doses of toxins, seeking immunity through careful experimentation. Historical accounts suggest he began with minute quantities, gradually increasing the dosage over time, a process later termed Mithridatism. He tested a variety of substances, from hemlock and arsenic to more exotic poisons derived from plants and minerals native to Anatolia and surrounding regions. This methodical exposure required not only courage, but meticulous observation as the king and his attendants documented the body's responses, seeking patterns that might indicate resistance. Such experimentation demonstrates an early practical understanding of pharmacology and the human body's capacity for adaptation. According to legend, dozens of herbal and mineral ingredients were blended with a precision that has been lost to history. Contemporary sources and later Roman writers speak of complex formulas incorporating gum resins, roots, bark, and metallic powders blended in exact proportions. Some ingredients may have had mild purgative or detoxifying effects, while others were chosen for their reputed protective qualities. The precise combination, preparation, and timing, however, were kept secret, entrusted only to the king and his closest alchemists. Over time, the recipe became more than a formula. It became a symbol of control over life and death, a silent assertion of mastery over the invisible forces that threatened his reign. Every ingredient of Mithridatium was selected with painstaking care, often harvested under precise conditions believed to enhance potency. Herbs were gathered at specific times of day or during particular lunar phases, reflecting ancient beliefs in celestial influence on efficacy. Minerals and metals were sometimes purified through repeated heating or grinding, processes that could alter chemical properties. Certain recipes suggest the use of ritual incantations or prayers during preparation, blending empirical observation with mystical practice. These careful techniques indicate that Mithridates' antidote was not merely a medicinal concoction, but a fusion of science, superstition, and royal ceremony, adding layers of complexity that modern researchers struggle to replicate. After Mithridates' fall, his formula travelled silently through the Mediterranean, copied, adapted, and eventually absorbed into royal pharmacopoeias. Roman physicians documented versions of the antidote, integrating it into medical texts that circulated widely across the empire. Byzantine and later Islamic scholars reference similar recipes, occasionally embellishing or substituting ingredients according to local availability. In each transition, the mixture retained its aura of secrecy and power, yet the original proportions and methods slowly eroded, leaving behind only fragments of what once may have been a precise, highly effective preparation. Through painstaking study, historians and toxicologists today can identify only pieces of the mixture and estimate the effects of its probable ingredients. Plants such as rue, poppy, and mandrake appear frequently in references, alongside minerals like antimony or gold dust, each with known pharmacological properties. Some ingredients could counteract specific toxins, while others may have served symbolic or ceremonial purposes. Attempts to reconstruct the formula reveal the sophistication of ancient pharmacology, yet even with modern chemistry, the exact interactions and intended outcomes remain uncertain. The partial knowledge that survives offers insight into early science, but underscores the impossibility of fully recovering the king's original antidote. All written records combined cannot restore the original antidote. Certainty remains out of reach. The recipes that survive are inconsistent, sometimes contradictory, and often incomplete. Ancient texts hint at precise dosing schedules and methods of preparation that likely required specialized knowledge and hands-on training now lost to time. Some historians argue that the formula may have been as much psychological as medicinal, instilling confidence in rulers and courtiers as much as providing physical protection. Whatever the case, the disappearance of the complete method leaves a gap in understanding that has fueled centuries of speculation. Mithridatium was more than medicine. It became a symbol of control over life, death, and the unseen threats that lurk in every court. Its legend inspired later monarchs, alchemists, and physicians to attempt imitation, each seeking to harness the elusive power of immunity. The antidote was woven into the cultural imagination as a safeguard against betrayal, a promise that knowledge could defy mortality itself. Even as the original formula faded, its story persisted, a cautionary tale and a testament to the ingenuity and obsession of a ruler who lived in constant fear, yet achieved a form of biochemical immortality. By the Middle Ages, the original recipe had vanished almost entirely, leaving only tantalizing references in the writings of apothecaries and historians. Scholars scoured texts for clues, noting ingredients, proportions, or methods that might approximate the lost antidote. Each attempt, however, revealed the limitations of surviving knowledge. Without the precise preparation, timing, and dosage, the antidote remained more legend than reproducible medicine. The mixture's disappearance serves as a reminder of how even the most critical and carefully guarded knowledge can vanish, leaving history with fragments that hint at mastery but conceal the full truth. Buried within the margins of ancient texts, the formula of Mithridates' universal antidote remains a puzzle that no modern hand has yet solved. Greek automatic temple doors. Devotees approaching a temple in ancient Greece would witness doors that moved without hands, their motion as if guided by unseen forces. In the flickering torchlight, the heavy wooden panels swung open with measured grace, startling worshippers and elevating the sacred atmosphere. To the ordinary observer, the movement seemed divine, yet behind the spectacle lay principles of physics carefully harnessed, concealed beneath the veneer of ritual and reverence. The doors transformed a simple entry into a ritual of awe, blending human ingenuity with the perception of supernatural intervention. The Hellenistic world was captivated by devices that blurred the boundary between art and invention, setting the stage for Heron's creations. Engineers and philosophers experimented with water clocks, moving statues, and self-playing organs, pushing the limits of what could be achieved with levers, pulleys, and flowing water. Temples and theatres alike showcased these inventions, impressing citizens and visitors with displays that merged entertainment, spiritual significance, and technical prowess. Heron drew inspiration from this rich environment, applying mathematical insight to create mechanisms that were both functional and astonishing in their effect. Heron of Alexandria, a mathematician and engineer, documented designs that could transform simple hydraulic principles into dramatic motion. Writing in the 1st century CE, he combined observation, experimentation, and mechanical theory to produce descriptions of devices that could manipulate doors, statues, and theatre scenery automatically. His understanding of pneumatics, siphons, and the behaviour of fluids under pressure reveals a civilization capable of blending mathematics, craftsmanship, and performance into seamless spectacle. Heron's texts survive in fragments, tantalizingly detailed yet leaving much to conjecture, as the practical knowledge of execution seems to have dissipated over time. The movement of the doors relied on a hidden network of weights, pulleys, and water-filled vessels, harnessing gravity and air pressure in perfect harmony. Heating a hidden chamber of air beneath a sealed container could expand the gas, displacing water and activating ropes that turned axles or rotated gears. Counterweights adjusted tension, ensuring smooth movement while preventing abrupt or dangerous swings. Although modern engineers can replicate simplified versions, the subtleties of Heron's designs, the exact ratios, vessel shapes, and timing mechanisms, remain speculative, and no ancient temple has survived intact with its automatic doors fully preserved. The doors were not merely mechanical curiosities, they were entwined with religious ceremony, responding to the lighting of fires or the presence of worshippers. Flames in an altar might heat a sealed air chamber, triggering the mechanism without direct human touch. The act of opening became part of the ritual itself, transforming a mechanical action into an extension of spiritual practice. Technology served not as spectacle alone, but as a conduit for religious awe, elevating ordinary stone and timber into living architecture that moved in harmony with divine observance. As the doors moved, the temple itself seemed to breathe, responding in sound and shadow to the rhythm of unseen hands. The creaking of timber, the subtle echo through stone corridors, and the glint of polished bronze fittings enhanced the perception of life within the building. Worshippers would interpret these movements as signs of divine presence, while priests subtly guided the ritual to maximize impact. The interplay of sight, sound, and motion illustrates how Heron's mechanism was integrated not only into engineering, but into the sensory and psychological experience of sacred space. Temples across the Mediterranean employed similar devices, though only scattered descriptions survive, leaving the full scope of their prevalence a mystery. Roman and later Byzantine texts occasionally allude to self-moving doors or statues, while archaeological evidence is largely absent. Other automatic mechanisms, from self-playing organs to rotating theatre stages, hint at an experimental culture fascinated by automata and engineered surprise. Yet despite these traces, the practical knowledge of precise construction vanished, leaving Heron's writings as the faint echo of a technology whose complexity outstripped most later attempts at replication. The precision required to balance hydraulics, timing, and structural forces underscores a level of craftsmanship that would challenge even modern restorers. Small variations in water volume, air pressure, or pulley alignment could disrupt the entire system. Every component, from polished bronze axles to sealed wooden vessels, demanded exacting attention, for a minor flaw could halt the doors entirely. Craftsmen likely required months of trial and adjustment, observing incremental changes and refining the design until the doors moved with the elegance described in surviving accounts. The combination of theory, material science, and hands-on problem-solving represents an advanced understanding that is almost incomprehensible given the tools of the era. By the time the Roman Empire waned, most automatic temple doors had vanished, their secrets preserved only in texts and fleeting references. The mechanisms, dependent on precise execution and continual maintenance, fell into disuse as workshops and knowledge were lost. Observers centuries later could marvel at the descriptions in Heron's manuscripts, but lack the skills, tools, and context to reproduce the effect reliably. What once inspired awe in worshippers became a curiosity for scholars and engineers, a technological ghost haunting the history of human innovation. At present, scholars and engineers can speculate and experiment, yet no temple doors move automatically as they once did in the flickering torchlight of ancient Greece. Replicas in laboratories and museums provide glimpses of the principle, but they fail to capture the scale, integration, and ritual significance of the originals. The gaps in practical knowledge underscore the fragile transmission of technical expertise across centuries, where a brilliant concept survives in writing while the living craft disappears. Each attempt to reconstruct these devices reinforces both admiration for the ancients and awareness of how much of their ingenuity is lost to time. In the shadowed workings of Heron, the secret that moved sacred doors hovers between memory and comprehension, untouched by modern hands. Roman dodecahedrons. Unearthed in fields, villa ruins, and forested riverbanks, the bronze dodecahedrons first captured the attention of scholars for their precise symmetry and hollow interiors. Each object, small enough to hold in a hand yet heavy with the weight of meticulous casting, seemed to embody a purpose that time had concealed. The 12 pentagonal faces, pierced by circular holes of varying diameters, hinted at deliberate design, while the absence of inscriptions or accompanying tools deepened the enigma. Though they have been scattered across Europe from Gaul to the Danube, their function has resisted explanation, leaving observers to marvel at craftsmanship that survived the centuries without a clear rationale. Each dodecahedron is carefully cast, demonstrating a level of skill that suggests specialized workshops or master artisans. The bronze is smooth and evenly finished, and despite centuries of corrosion, the forms retain the precise geometry intended by their makers. No two examples are exactly alike, implying local variation or customization, yet all share the same 12-sided structure, balancing uniformity with subtle uniqueness. The holes in each face, perfectly circular, range in diameter from small to large, offering clues to possible mechanical, measuring, or symbolic purposes, while simultaneously frustrating attempts to reconstruct their original use. From Gaul to Pannonia and beyond, the distribution of dodecahedrons spans the Roman Empire in ways that hint at a shared culture, trade network, or military connection. Finds are often isolated, discovered in rural settlements, along roads, or in abandoned forts, suggesting portability and deliberate placement. The geographical spread implies that these objects were known beyond a single region or city, yet the lack of contemporary references in Roman literature leaves their story largely unwritten. Archaeologists piece together fragments of evidence, noting patterns in location and form, but the true significance of these objects continues to evade clear understanding. Scholars have proposed countless uses over the centuries: candle holders, tools for measuring distances or calibrating surveys, gaming devices, or instruments for divination and ritual. Each theory draws from the shape, hole sizes, and portability, yet no single explanation accounts for all examples. Some suggest the dodecahedrons served multiple purposes, adapting to context or user, while others argue that they carried ceremonial or symbolic weight that modern interpretation cannot fully grasp. Some experiments suggest the dodecahedrons might have measured land, distances, or even celestial angles, though each trial only deepens the uncertainty of their original role. Attempts to replicate these functions reveal the object's precision and complexity, yet none provide definitive answers, leaving the central mystery intact. If functional, the dodecahedrons required deliberate handling and care, implying that they were intended for specialized tasks rather than casual use, where patterns on certain edges suggest repeated manipulation, while the distribution of oxidation indicates exposure to varying environments, possibly outdoors or in semi-permanent installations. Their size allows for portability, yet the careful balance of weight and form hints at a purpose that demanded precision. Each detail, from the smoothness of bronze surfaces to the exactness of drilled holes, conveys intention, yet that intention remains obscured by the absence of any explanatory record. For all the digging and study, the significance of the settings in which dodecahedrons appear is still unclear. They are seldom accompanied by tools, inscriptions, or other artifacts that might reveal function. Archaeologists rely on fragmentary evidence, the positioning of objects, patterns of wear, and the occasional association with Roman villas or military sites. These clues, while suggestive, fall short of definitive interpretation, leaving each discovery to raise more questions than it answers. The objects are reminders of how much of ancient life, even in a civilization as documented as Rome, can disappear from the record, leaving gaps that challenge understanding and imagination alike. In the absence of practical explanations, some scholars have turned to symbolism, proposing that the dodecahedrons encoded celestial patterns, numerology, or abstract principles of harmony. The recurrence of 12 faces may not be a coincidence, hinting at philosophical or cosmic significance that remains invisible to modern eyes. The number 12 held weight in Roman calendars, astrology, and societal organization, and it is possible that these objects functioned as symbolic or ceremonial tools, aligned with broader cosmological or numerological thought. Yet, despite these educated hypotheses, the true meaning of the dodecahedrons remains unreachable, preserved only in speculation. Collectors, historians, and engineers alike are drawn to Roman dodecahedrons, yet their purpose remains stubbornly unclear despite modern techniques. Recent studies employing 3D modelling and metallurgical analysis have revealed intricate details of casting, wear, and distribution, yet the overarching function remains beyond reach. Replicas can demonstrate potential mechanical applications or geometric properties, but no experiment can fully capture the context in which these objects were originally employed. Each new find renews curiosity, inviting speculation and study, yet the essential truth, the practical or symbolic meaning intended by their creators, remains unclaimed by history. Their silence is absolute, yet insistently present, challenging every effort to impose certainty on a design that once served a purpose now lost to time. The 12 faces and measured openings persist as a riddle across centuries, defying understanding while hinting at knowledge the Romans took with them into oblivion. Sumerian water clock. Ages prior to sundials cast shadows on temple walls, the Sumerians harnessed the steady flow of water to mark the passage of hours. In bustling city centres and sacred precincts alike, time was not abstract but measured, tangible in the rhythm of droplets descending through carefully calibrated vessels. The clepsydra, or water clock, transformed a simple principle of physics into a tool of governance and ritual, bridging the practical needs of daily life with the reverence of sacred observance. Each vessel contained the promise of order, yet the precise knowledge required to maintain its accuracy has largely vanished, leaving modern scholars to reconstruct its operation from fragments and inference. Shards of clay, each etched with precise markings, reveal a sophisticated understanding of how water could be measured and managed. Excavations at Ur, Lagash, and other Sumerian cities have revealed basins with notches, channels, and calibrated lines, all intended to translate an invisible, continuous process into quantifiable intervals. The clay shows signs of repeated use and careful shaping, indicating that these objects were not experimental toys but functional instruments maintained over the years. Minute differences in size and marking suggest local adaptation, while the uniformity of principle hints at a shared understanding of time across the region. These vessels were not idle curiosities. They regulated the rhythms of temple rituals and civic administration alike. Priests and officials would rely on the measured flow to dictate the start of offerings, judicial hearings, or civic announcements. By controlling time with water, the Sumerians could synchronize events across spaces that lacked visual cues like shadows or mechanical bells. Seasonal variations and temperature shifts were accounted for, likely through careful observation and incremental adjustment, demonstrating a level of empirical reasoning that presaged later engineering traditions. Holes, channels, and carefully shaped basins guided each drop, translating the invisible flow into measurable intervals. In some examples, the vessel's base included a narrow outlet that allowed water to exit at a regulated pace, while surface markings recorded the passage of each hour. Adjustments could be made by adding or restricting flow, ensuring that ceremonies remained aligned with intended temporal divisions. This manipulation of natural forces required not only technical skill, but an intimate familiarity with the materials and environmental conditions, revealing a practical intelligence that intertwined observation, experimentation, and ritual practice. Delicate adjustments in the design of some vessels suggest that Sumerian artisans monitored the movement of liquids with extraordinary care. Discuss evidence that the Sumerians accounted for variables like water temperature, impurities, or sediment that could affect flow. Note that some clepsydras show evidence of repair or modification, implying they were maintained and recalibrated over time. Highlight that these small refinements indicate a sophisticated empirical understanding, blending observation, experimentation, and hands-on management to achieve reliable measurement. Time itself was entwined with the divine, and the water clock became a bridge between human activity and celestial order. Temple ceremonies, agricultural schedules, and even astrological observations depended upon its measured flow. The Sumerians believed that order in the heavens mirrored order on earth, and controlling time with water provided a means to harmonize mortal actions with divine patterns. Each measured interval carried significance, whether for maintaining the correct rhythm of offerings or ensuring that civic duties proceeded without discord, linking engineering and spirituality in a subtle, enduring partnership. The principles of the clepsydra echoed through later civilizations, influencing Egyptian, Babylonian, and Greek timekeeping alike. Water clocks spread along trade routes and were adapted to local needs, evolving in form while retaining their underlying logic. The Sumerian approach, however, remains particularly striking in its combination of simplicity and sophistication. A vessel, a calibrated flow, and the careful hand of the observer were enough to control time in a world without mechanical clocks. Yet as centuries passed, the skill to construct and maintain such devices faded, leaving only archaeological traces and the faint echo of regulated hours. Surviving pieces and records offer clues, yet much about Sumerian water clocks continues to elude understanding. Scholars debate the precise calibration, the frequency of maintenance, and the exact social contexts of their use. Some vessels appear ceremonial, while others may have been purely practical. The lack of consistent inscriptions or detailed records leaves interpretation necessarily speculative, and yet each new find offers a glimpse into a culture deeply invested in measuring, controlling, and revering the passage of time. The water clocks are both evidence of human ingenuity and a reminder of how easily technical knowledge can slip through the cracks of history. Replicas attempt to restore the rhythm of ancient hours, but the meticulous timing of the originals resists duplication. Experimental archaeologists pour water into carefully modelled vessels, adjust flow, and observe the passage of minutes. Yet even with modern tools, the exact rhythms achieved by Sumerian priests remain uncertain. These experiments illuminate the complexity of a seemingly simple concept and evoke a sense of wonder at the intelligence and patience required to harness such a fragile, continuous force. The clepsydra stands as a testament to human curiosity, a device that measured the intangible and left only the whisper of its purpose for future generations to ponder. The water once guiding Sumerian hours has long evaporated, leaving only the silent enigma of its exact rhythm to challenge every hand that seeks to revive it. Olmec Magnetic Compass. During excavations along the winding rivers of Mesoamerica, small stones with unusual properties emerged from the earth, compelling observers to wonder at their significance. Unearthed among ceremonial mounds, village sites, and riverbanks at Olmec centers like San Lorenzo, La Venta, and Tres Zapotes, these dark, polished minerals resisted simple explanation. Their smooth surfaces, occasional perforations, and subtle shaping suggested deliberate modification, yet it was a hidden property that would capture attention across centuries, an invisible force pulling subtly, aligning themselves when set upon a flat surface. For a civilization that left no written records of magnetic theory, such stones hinted at an intuition both practical and enigmatic, offering glimpses of understanding now lost to time. Tests revealed an unexpected pull, a force neither visible nor explained by the observers, drawing attention from archaeologists and physicists alike. Modern analysis confirmed that some of these stones contain naturally magnetized iron ore or lodestone, capable of interacting with the Earth's magnetic field. Experiments demonstrated that when free to rotate, they tended to orient along a consistent axis, a phenomenon familiar to compasses but centuries ahead of known invention elsewhere. Yet even with these insights, the context of their use remained obscure, leaving room for speculation about navigation, ritual, or both, as the stones seemed to bridge the practical and the mystical. Rivers carved pathways through dense forests, guiding trade and settlement, and the magnetic stones may have helped the Olmecs navigate these shifting waters. Canoes and rafts plied complex tributaries, transporting jade, obsidian, and other valuable commodities, while overland journeys required orientation through a dense jungle landscape. It is plausible that the Olmecs used these magnetic minerals as rudimentary guides, maintaining consistent direction on unfamiliar routes or aligning camps and temporary structures. The combination of environmental necessity and human ingenuity hints at a civilization attuned to subtle natural forces, observing patterns that ordinary sight alone could not reveal. In such landscapes, even slight misdirection could mean hours of delay or the loss of precious goods, lending practical urgency to what may appear to modern eyes as a simple curiosity. Some stones were placed alongside temples and ceremonial mounds, their arrangement hinting at a careful relationship to the cardinal points. Excavations suggest that these placements were not random. Certain lodestones align with east-west or north-south axes, corresponding to sunrise, sunset, or the rising of significant stars. In La Venta, for example, small magnetic stones were found near the foundations of monumental platforms. While at San Lorenzo, clusters of polished minerals occupy positions that suggest deliberate spatial planning. Whether used as markers for ceremonial processions, astronomical observations, or sacred rituals, the stones demonstrate a deliberate spatial intelligence. Their presence blurs the line between science and belief, suggesting that Olmec understanding encompassed both practical guidance and cosmological awareness, even if the full meaning remains beyond modern comprehension. Polished and shaped, these stones retained their magnetic pull, hinting at careful selection and manipulation. Some show evidence of repeated handling, smoothing, and minor recarving, implying that they were not merely natural curiosities but valued implements. Laboratory tests confirm that variations in magnetization and orientation would have made some stones more reliable than others, suggesting that the Olmecs knew which materials to prefer for specific tasks. In a world without compasses, subtle differences in natural magnetism could provide a remarkable advantage in aligning structures, guiding travel, or orchestrating rituals, revealing a sophisticated understanding of material properties that survives only as a tantalizing trace. No record survives of how the Olmecs might have used these stones to guide journeys or ceremonies, leaving each method to conjecture and experimental reconstruction. Scholars have floated theories ranging from navigation along rivers to surveying land for monumental construction, and modern simulations confirm that even small stones, carefully handled, could provide consistent directional information. Attempts to replicate their use reveal the subtlety of the technique. Slight tilts, water tables, and surface friction all affected accuracy, implying that the original practitioners possessed finely honed observational skills. Some experimental setups even suggest that paired stones might have been used to align processions or track ceremonial timings in relation to celestial events. Every experiment deepens appreciation for the technical and cognitive sophistication embedded in what might appear at first glance to be a simple rock. The presence of these magnetic stones reveals a civilization attuned to forces beyond immediate perception, blending observation, spiritual practice, and environmental understanding. The Olmecs may have conceived of magnetism not as a purely mechanical property, but as a force intertwined with natural and supernatural realms, capable of guiding humans in both the tangible and symbolic landscapes. Such awareness speaks to a culture that observed and interpreted patterns meticulously, combining sensory experience with abstract reasoning in ways that left no written explanation yet profoundly influenced settlement, travel, and ritual activity. The careful placement of stones near rivers, mounds, and ceremonial platforms suggests that their significance extended beyond navigation into realms of communal identity and sacred geography. Each discovery renews fascination, yet the precise function of these stones remains locked in a past that refuses explanation. While the artifacts endure, their secrets are invisible, encoded not in inscriptions or tools, but in arrangement, orientation, and interaction with the world around them. Researchers can measure magnetic pull, trace alignments, and hypothesize applications, but the Olmecs' intentions, the methods by which they employed these stones, and the full scope of knowledge they implied are irretrievably lost. Even as technology brings clarity to the material properties, the lived understanding, the practical and spiritual reasoning guiding their use, remains veiled, leaving a silent challenge for every modern hand that seeks to comprehend it. The stones continue to mesmerize, standing as a mute testament to a wisdom that predates the compass. They challenge modern observers to consider how early civilizations perceived the unseen, and how knowledge could be both applied and deliberately concealed within culture. Each magnetic artifact, ordinary in appearance yet extraordinary in function, embodies a fragment of understanding that vanished with its makers, leaving an enduring riddle across centuries and continents. The pull embedded in these ancient stones persists across time, hinting at mastery over unseen forces that vanished with the Olmecs themselves. Greek fire siphon. In the crowded docks of Constantinople, a weapon emerged that seemed to defy the very elements it wielded. Historians attribute its invention to Kallinikos, a Syrian engineer or chemist, who presented the Byzantines with a formula and device that transformed naval warfare forever. Greek fire, as it came to be known, was a liquid incendiary capable of burning upon water, an anomaly that startled friend and foe alike. Contemporary chroniclers marvelled at its potency, describing fleets engulfed in flames and the panicked cries of sailors witnessing an inferno that could neither be contained nor fully comprehended. Even in its earliest deployments, it carried with it a dual legacy of tactical brilliance and inscrutable mystery. Mounted on wooden frames or cradled in bronze tubes, siphons projected the fiery liquid with terrifying precision. These devices were compact enough to be handheld in some instances, while larger, more elaborate contraptions adorned the decks of galleys, allowing operators to spray the incendiary onto enemy vessels. The mechanics relied on pressure, often hydraulic or pneumatic, to propel the combustible mixture, yet no complete example survives, leaving modern reconstructions to depend on fragmentary texts and illustrations. The ingenuity of this mechanism, combining chemistry and engineering in a period centuries before modern fluid dynamics, exemplifies the ingenuity of Byzantine military thought, while the absence of a surviving device preserves the shroud of mystery around its operation. The chemical formula, recorded only in fragments, combined substances whose proportions remain speculative to this day. Historical sources hint at a mixture of naphtha, quicklime, sulfur, and various resins, but the precise ratios and treatment methods were carefully guarded secrets, jealously protected by the Byzantines. Scholars have attempted to recreate the mixture, yet every experiment illustrates the challenge of matching the weapon's reputed performance. It's not merely the fire itself that mystifies, it is the controlled projection, the ability to spray it across distances without self-immolation, that confounds modern engineers. The secretive transmission of the formula ensured that Greek fire remained an unreplicated marvel, a combination of practical knowledge and cunning concealment. Fires leapt across the waves as Byzantine galleys confronted enemy fleets, their effectiveness magnified by both surprise and psychological terror. Accounts from the siege of Constantinople and battles along the Mediterranean describe flaming, liquid-consuming ships almost instantly, sowing panic and confusion among opposing sailors. Even well-prepared forces found themselves helpless, unable to extinguish the flames with water and unable to anticipate the trajectory of the streams. The weapon's efficiency did not rest solely in its chemistry or mechanics, but in the tactical mastery with which commanders deployed it, turning a scientific marvel into an instrument of near-mythical warfare. Opponents recoiled, not only from the flames but from the mystery that shrouded the weapon's operation. Observers could not discern how a liquid could continue burning atop water, or why Byzantine crews remained relatively safe while projecting it. This uncertainty amplified fear, transforming Greek fire into a psychological weapon as much as a physical one. Chroniclers noted that entire fleets hesitated or retreated upon encountering its presence, and rumours of divine protection or sorcery clung to the device. Its reputation, carefully cultivated or inadvertently amplified, became a strategic tool in itself, proving that the perception of invincibility can be as powerful as the weapon's actual effect. Specialist crews trained in silence tended the siphons, their expertise as jealously guarded as the formula itself. These men and artisans formed a living firewall around Greek fire, drilled not only in pumping and aiming but in the hazardous choreography of fueling, pressurizing and cleaning the devices under combat conditions. Sources and later chroniclers imply that operators learned how to stoke bellows, manage pressure vessels, and predict wind behaviour so the spray would travel to the enemy and not back upon their own decks. Supplies of combustible oils and naphtha were kept in sealed amphorae and guarded by imperial crews, often sourced from eastern regions where bituminous fuels were available, while maintenance squads kept bronze nozzles clear of residue and repaired wooden frames between sorties. Byzantine law and custom appear to have treated knowledge of the weapon as state property, and punishment for divulging secrets could be severe, underlining how the human systems of training, logistics and discipline were integral to Greek fire's terrifying effectiveness. Later generations sought to reproduce the Inferno, but texts and experiments revealed only frustration and incomplete understanding. Medieval engineers, faced with scattered instructions and ambiguous diagrams, could achieve only limited successes, while modern chemists attempting reconstruction note that small variations in ingredients drastically reduce the incendiary's effectiveness. Even the siphons themselves, requiring both careful craftsmanship and precise pressure management, resisted replication. Every failure underscores the deliberate genius of Byzantine secrecy, a civilization that mastered a force of nature and ensured that its secrets would vanish with those who knew them. Despite centuries of study, the precise mechanics and composition of the Greek fire siphon remain locked in the shadows of history. Scholars debate whether some ingredients have been permanently lost, or if the original processes depended on subtle handling techniques impossible to deduce from surviving records. Archaeological fragments, often corroded or incomplete, hint at the materials used in the siphons, yet they reveal little about the operational skill required. Modern understanding of flammable liquids and fluid propulsion only begins to approach the sophistication implied by historical accounts. Greek fire endures as a reminder that technological mastery can exist in forms that vanish, leaving only awe and speculation behind. Today, the siphons themselves survive only in imagination, sketches, and occasional fragments, yet their legacy continues to captivate historians, chemists, and military scholars alike. Greek fire challenges assumptions about the sophistication of medieval science, illustrating that knowledge can be both immensely practical and perilously transient. Each account, each reconstruction attempt, reinforces a paradox. The weapon was both known and unknowable, real in its destructive power yet hidden in method. In every detail, the siphon symbolizes a fleeting mastery over chemistry, engineering, and tactical genius, preserved only through narrative memory and the lingering fascination of those who study it. The flames that once leapt from Byzantine siphons endure only in memory, leaving a volatile secret unclaimed by time. Incan earthquake-proof masonry. Stone walls, crafted with such precision that they have survived centuries of tremors, form the backbone of a civilization lost to time. These constructions, found at Machu Picchu, Ollantaytambo and Cusco, reveal a mastery over stone and landscape that continues to baffle modern engineers. Unlike walls built from mortar, Incan masonry relies on interlocking stones, carefully shaped to fit one another with almost invisible seams. Travellers and chroniclers alike have marvelled at how these structures endure earthquakes that topple modern buildings, their surfaces smooth and corners polished, yet imbued with a subtle flexibility that seems to anticipate each seismic shift. The walls stand as silent witnesses to both the ingenuity of their builders and the mysteries they left behind. Each block is shaped to nestle against its neighbour, trapezoids and irregular polygons forming a puzzle engineered to endure. The trapezoidal design, wider at the base and narrower at the top, allows walls to resist both vertical and lateral forces, while the careful selection of shapes distributes stress across entire structures. Stones vary in size from small blocks to massive monoliths weighing several tons, yet each is precisely cut to bear weight evenly and maintain alignment through centuries of tremors. Modern architects study these forms not only for their aesthetic appeal, but for the principles of stability embedded in their design, though no contemporary method fully replicates the efficiency observed in Incan construction. Stones are polished, corners beveled, and joints so precise that even a knife cannot be inserted between them. Artisans shaped the rock with stone hammers, bronze chisels, and abrasion, leaving surfaces that fit with an almost mystical accuracy. The labour involved extended beyond individual blocks. Entire terraces were aligned with topographical and astronomical precision, creating a cohesion that bound walls plazas and temples into a single harmonious framework. Scholars note that the degree of finishing, often invisible to casual observers, suggests a profound understanding of both the physical properties of stone and the environmental challenges posed by the Andes. The result is a masonry that is both practical and sublime, a tactile record of knowledge lost to history. The journey of each stone began long before it reached its place in the wall, quarried from mountainsides and guided across terraces with careful planning. Massive blocks were extracted using stone hammers, wooden wedges and controlled splitting, then transported over uneven terrain without wheels, likely relying on teams of labourers, ropes and inclined planes. In some cases, stones weighing several tons were manoeuvred along precisely levelled terraces or wooden sledges lubricated with water or clay, demonstrating an understanding of leverage and force distribution beyond what is commonly attributed to pre-Columbian societies. Evidence at quarry sites shows tool marks consistent with sequential cutting and shaping, indicating that masons anticipated both the weight and orientation of each block well in advance. This painstaking orchestration between quarrying, transportation and placement underscores a level of logistical sophistication as critical to the masonry's endurance as the fitting of the stones themselves. When the earth quakes, terraces shift, yet walls remain upright, a silent testament to engineering foresight. Historical accounts record earthquakes that devastated neighbouring regions, toppling buildings and scattering ruins, while Incan construction stood firm. The wall's slight give allows them to absorb shocks rather than fracture, a technique perfected through careful selection of stone, friction-fit placement, and tiered terracing. Each structure becomes a dynamic system, moving subtly without compromising integrity, a feat that demonstrates not only technical skill, but an intimate observation of natural forces. The endurance of these walls continues to inspire architects and engineers who struggle to reconcile ancient methods with modern building science. Construction was not merely practical, it reflected cosmic order, labour organisation, and reverence for the mountains themselves. The placement of stones often aligns with solar events, sacred peaks, and ceremonial centres, integrating function with ritual. Labourers worked in teams under strict supervision, ensuring both accuracy and symbolic significance, while artisans trained in specialised techniques handled the most delicate or massive stones. In this way, the walls convey both the physical strength and the spiritual vision of the Inca, whose cities were built to mirror the harmony they perceived in the natural world. The integration of social, cultural, and technical knowledge exemplifies a civilization whose ingenuity was inseparable from its worldview. No manual survives, and the methods of cutting, fitting, and aligning stones vanished with the conquest, leaving only the silent testimony of surviving walls. Spanish chroniclers marvelled at structures they could neither replicate nor fully comprehend, recording the precision without understanding the techniques behind it. Archaeological studies reveal traces of tool marks and quarrying strategies, yet the full methodology, the precise angles, friction calculations, and fitting sequences remain speculative. Modern experiments using contemporary tools demonstrate that replicating even a single section of Incan wall with equivalent resilience is exceptionally challenging, a testament to knowledge refined over generations and now largely erased from living memory. Every terrace that withstood centuries of tremors and every collapsed wall nearby underscores the ingenuity that once flowed through Incan hands. Observation of surviving structures reveals subtle variations in stone placement, minor gaps intentionally left to allow movement, and weighted alignment designed to maintain stability. These details, invisible without careful study, indicate a system of construction rooted in empirical observation, trial, and refinement rather than theoretical calculation. The very presence of fallen walls nearby accentuates the skill behind those that remain intact, emphasizing both the human mastery and the unpredictability of the natural forces they sought to counter. In these silent ruins, one perceives a dialogue between earth and architect that continues to challenge understanding. The stones hold secrets of hands attuned to the restless mountains, a knowledge that vanished yet whispers through every enduring wall. Viking Sunstone. Amid the harsh, icy coasts of Scandinavia, where longships once slipped through fog-like shadows, the story of the Viking Sunstone quietly begins. Navigators of the 9th and 10th centuries relied on the skies for guidance, yet the northern latitudes offered long nights, dense clouds, and storms that blurred the horizon. Amid these treacherous conditions, a tool emerged that modern historians can scarcely reconstruct: a crystalline stone said to reveal the position of the sun even when it was hidden. References to this device appear in the sagas and in the marginal notes of medieval manuscripts, describing a method of polarizing light that allowed seafarers to discern cardinal directions when the sky was overcast. The sunstone, sometimes thought to be made from Iceland's spar, cordierite or tourmaline, provided a way to navigate by detecting the sun's rays filtered through clouds and fog, a subtle manipulation of natural light that vanished from practical use after the Viking Age. Accounts of the sunstone suggest that its use was both routine and secretive. It was small enough to fit in a navigator's hand, yet precise enough to prevent error during long voyages across the North Atlantic. The sagas hint at ceremonial aspects, though it's unclear if these were literal or metaphorical. Scientists in recent decades have recreated the principle of light polarization, demonstrating that a crystal such as Iceland spar can indeed reveal the sun's position at different times of day. By rotating the crystal until the light transmitted through it was balanced, a shadowed disk on the stone would indicate the direction of the sun. The physical traces of sunstones are elusive. No confirmed Viking-era specimens have been recovered from archaeological sites, though some crystals found in shipwrecks and hoards may correspond to the descriptions. Written sources, like the account of a Norwegian bishop in the 12th century, suggest that seafarers could read the sky through these stones even on overcast days, aligning themselves with the sun without ever seeing it directly. In these conditions, a sunstone could mean the difference between survival and becoming a ghost of the Atlantic. Modern experiments confirm that Iceland spar can reveal the sun's position under diffuse light, a method likely discovered by seafarers empirically. The use of sunstones also intertwines with the broader knowledge of Viking maritime technology. Longships were marvels of construction, designed for speed and maneuverability, and their crews possessed an intimate understanding of tides, currents, and seasonal wind patterns. It was complemented by other tools such as the sun compass, a wooden disc that indicated the sun's movement, and the stars, whose positions were memorized for months at a time. Together, these methods formed a navigational system rivaling later European instruments. The sunstone represents a single point of light within a constellation of Viking ingenuity, a technology that vanished as the practical knowledge of seafaring sagas faded and the manuscripts documenting it were lost or misinterpreted. Modern research has also suggested that the sunstone may have served multiple purposes beyond navigation. Some experiments indicate that polarizing crystals could have been used to check the clarity of the air, measure angles of the sun to determine the season, or even assist in predicting weather patterns. The precise techniques remain speculative, yet they hint at a culture in which observation, craft, and natural materials were integrated into practical science. Unlike other technologies, the sunstone left no continuous record of instruction. Its secrets disappeared when the oral traditions of seafaring were disrupted, and when written references were dismissed as anecdotal or mythic by later scholars. The mystery of the sunstone is compounded by the atmospheric conditions in which it operated. The North Atlantic is notorious for sudden fogs, storms that arrive without warning, and a sky that alternates between brilliant sun and endless grey. For a navigator relying on memory, the sea could be unforgiving, yet the sunstone provided a method to read invisible patterns of light, to interpret the sky even when it refused to reveal itself. This ability would have been invaluable during long voyages to Iceland, Greenland, and Vinland, where coastal landmarks were rare and the ocean extended into endless horizons. Archaeologists and historians reconstructing these voyages note that surviving manuscripts offer only fragmented insights, emphasizing the difficulty of separating legend from practical application. The sunstone remains a vanished instrument, hinting at knowledge lost to time. Searches today lead to shipwrecks, Viking ruins, and hidden hoards, yet the sunstone itself has never been positively identified. Scholars rely on experimental archaeology, polarimetric studies, and textual analysis to infer its function. Iceland spar has been identified in medieval contexts, yet whether it was used intentionally for navigation or as a decorative or ceremonial object remains unclear. The lack of surviving examples underscores the fragility of technologies reliant on both material and oral transmission. The sunstone embodies an intersection of natural phenomena, craftsmanship, and human ingenuity, a device that could reveal unseen truths but whose practical knowledge dissipated with the seafarers who once relied upon it. Even as science and experimentation bring us closer to understanding its function, the sunstone remains a shadowed relic, a technology glimpsed only in fragments of writing, legend and light filtered through crystal. Its disappearance illustrates the fragility of knowledge across generations, particularly when reliant on ephemeral practices and perishable materials. Experiments and saga readings bring researchers closer, yet the full technique remains out of reach. The stone that once cut through fog and guided ships across the Atlantic is now a spectre, its secrets preserved only in the interplay of light and imagination. Out in the North Atlantic, beneath skies that stretch unbroken, the sunstone lies in silence, waiting to be found. Roman Hipparchus system. In the chill of Roman winters, warmth was a luxury few could claim without invention. Villas perched on hillsides and bathhouses in bustling cities required more than simple fireplaces. They demanded a system capable of distributing heat beneath stone floors and through walls. The Hipparchus emerged as a solution, a network of channels, pillars and furnaces that transformed fire into an invisible current, circulating warmth throughout structures without the visible presence of smoke or flame. For the Romans, comfort was not merely practical, it was a demonstration of engineering mastery and social order, a quiet assertion of control over nature and environment. Yet the intricacy of the system made it fragile, and its disappearance would reveal just how dependent civilization could be on human skill and knowledge. Engineers adapted ideas from Greek predecessors, experimenting with fire and airflow in ways that would echo for centuries. Early designs combined observation of heat behavior with clever construction. Hollow floors raised on pillars, flues built into walls, and furnaces that fed warm air under precisely calculated pressure. Romans learned to manipulate these currents with astonishing precision, a science of heat that required both experience and intuition. Texts from Vitruvius describe principles of construction, while archaeological evidence shows furnaces aligned with wall cavities to distribute air evenly. The system was not born fully formed, but evolved through trial, observation, and the practical demands of urban and domestic life, a testament to Roman ingenuity. Though unseen beneath the floors, a calculated labyrinth of pillars and channels carried warmth with exacting care, essential to the structure's function. The floor tiles, suspended on stacks of brick columns called pillae, allowed warm air to circulate freely, while flues built into the walls carried rising heat into rooms above. Furnaces, often located in the service area of bathhouses or private wings, required constant stoking, and temperature control depended on both fuel quality and skillful operation. In some villas, engineers combined water heating with hypercausts, creating baths that were simultaneously warmed and flowing, blending thermal engineering with hydraulics. The result was a network that produced not just warmth, but a consistent enveloping comfort that transformed architecture into a living, responsive organism. The pulse of the Hipparchus extended beyond comfort, marking the divide between private opulence and public austerity. In public bathhouses, Hipparchus enabled hot rooms, saunas, and tepid pools, offering citizens spaces for hygiene, conversation, and leisure. Wealthy families in their private villas could claim the luxury of continuous warmth, even in the depths of winter, a subtle reminder of social hierarchy embedded in architecture. The engineering mastery behind these systems was as much about status as utility. Maintaining an effective Hipparchus required knowledge and labour, resources only the affluent could consistently command. Heat in this context became a symbol of influence, a quiet dominion over both body and environment. Every brick and tile carried risk. A misaligned flue or neglected furnace could plunge a bathhouse into bitter cold. Maintenance was constant, and knowledge had to be passed from master to apprentice. The system's complexity made it vulnerable to human error and political upheaval. When skilled engineers were no longer available, or funding and attention waned, the Hipparchus quickly lost effectiveness. Archaeological surveys show ruins with scorched tiles and collapsed floors, fragments of what had once been precise, reliable networks. The fragility of the Hipparchus underscores how much of Roman civilization depended on accumulated expertise that could vanish within a generation. Ruins reveal hollow floors and scorched walls, silent witnesses to an engineering art lost to time. Excavations in Pompeii, Herculaneum, and across the Roman Empire show the remnants of the hypocaust: brick pillae, channel-lined walls, and furnaces partially preserved under layers of ash or centuries of soil. These traces hint at the scale and sophistication of the systems, but tell little about the daily routines required to operate them. Written manuals provide only partial guidance, while material evidence remains fragmentary. Scholars must reconstruct both structure and function through inference and experiment, piecing together a vanished practice from the scattered clues that endure in the archaeological record. When Rome fell, the knowledge of circulating heat slipped into obscurity, preserved only in scattered texts and the foundations of deserted villas. The collapse of centralized governance and trade networks meant that specialized skills were lost, and the labor-intensive maintenance of hypocausts could no longer be supported. Over time, the floors collapsed, flues clogged, and furnaces crumbled, leaving only hints of the once pervasive warmth. The technology did not merely disappear, it became inaccessible, its understanding buried beneath centuries of decay, leaving later generations to marvel at descriptions without the means to replicate them accurately. Civilization had moved forward, yet in its wake something remarkable had quietly vanished. While contemporary reconstructions illuminate ancient skill, they fall short of conveying the living warmth coursing through stone and mortar. Experiments with recreated hypocausts demonstrate the efficiency of the systems, the careful calculation of airflow, and the control of temperature that the Romans achieved without modern thermometers. Yet even these reconstructions cannot replicate the full sensory and social reality. The soft warmth in a winter bathhouse, the controlled rise of heat in a private villa, the subtle pleasure of engineering made tangible. Each experiment is a reminder of what knowledge was lost, of how human ingenuity can endure in fragments yet leave a profound absence in everyday life. The streets of abandoned cities conceal more than rubble. They hide the silent mastery of vanished engineers. Greek Archimedes' screw variants. Across fields and valleys, water flowed where it would, indifferent to human ambition, until someone sought to redirect it. In the arid landscapes of ancient Greece and along the banks of rivers that could flood or dry unpredictably, the challenge of controlling water became urgent, shaping the fortunes of settlements and crops alike. Channels and canals offered partial solutions, but lifting water from one level to another required ingenuity that few had yet mastered. It was in this context that the screw, a simple yet profound invention, emerged. Not merely a tool, but a revolution in manipulating one of nature's most capricious elements. The device transformed labour, enabling humans to channel water with efficiency and predictability, though the full variety of its ancient applications would fade from memory over the centuries. In the port of Syracuse, Archimedes lifted water as if by magic, turning an abstract spiral into a tool of extraordinary utility. According to historical accounts, he demonstrated the principle by raising water from ships' bilges or local wells, impressing contemporaries with a mechanism both elegant and practical. The screw relied on a helical surface inside a cylinder or trough, turned by manual or animal power, translating rotational motion into the upward movement of water. Archimedes' insight combined geometric reasoning with applied mechanics, creating a machine that could operate continuously, drawing water efficiently from wells, rivers, or flooded fields. It was a tangible demonstration of human intellect bending the natural world to deliberate purpose, a technology whose fundamental principle persists even today. From mines in Hispania to irrigation channels in Egypt, engineers modified the screw to meet diverse demands, yet the details of these innovations are lost to time. Evidence suggests that different lengths, diameters, and pitches were employed to optimize for flow rate, elevation gain, and local materials. While some screws were constructed entirely of wood, others reinforced with bronze or lead. Hellenistic engineers experimented with configurations that allowed the device to function horizontally or at a slight incline, adapting to terrain and task. Descriptions in texts, such as those by Vitruvius and later Roman authors, hint at ingenious applications for drainage, agriculture, and flood control, but no complete variant has survived intact, leaving the scope of experimentation largely to speculation. Wood, bronze, and ingenuity combined in spirals that twisted against gravity, a testament to both mechanical knowledge and practical skill. The construction of a screw required careful alignment of the helical blade, precise fitting within its trough, and attention to water tightness and friction, all without standardized measurements. Artisans relied on empirical observation, adjusting pitch, diameter, and rotation to achieve optimal performance. In some mining operations, multiple screws were installed in series to lift water over significant vertical distances, a feat of coordination and planning that demanded both engineering foresight and labour management. The machines were not mere tools, they were integrated into systems that reshaped the environment and enhanced human capability in tangible ways. Beyond familiar applications, the screw found its way into early water lifting devices, powering fountains, public baths, and experimental aqueducts. Records from Hellenistic Alexandria hint at attempts to couple multiple screws in tandem, creating cascades that lifted water over complex terrain, while Greek texts describe portable variants small enough to be carried by hand for temporary irrigation. These adaptations reveal a culture willing to experiment with scale and context, yet most designs disappeared with the fall of the city-states and the loss of practical instruction. Each lost variant suggests a dimension of hydraulic engineering now invisible, a silent testament to creativity that could manipulate water in ways the modern mind can scarcely visualize. Entire fields and towns relied on these machines, their productivity and survival intertwined with the silent rotation of screws moving water. In irrigation, the devices expanded arable land, allowing crops to flourish where rainfall was insufficient or unpredictable. In mining, they removed water from shafts, enabling the extraction of minerals critical for coinage, construction, and technological development. Even small communities depended on manually turned screws to supply drinking water or maintain gardens. Mastery of the screw thus conferred both practical advantage and social leverage, a subtle but persistent influence that shaped human settlement patterns and economic activity, though the full reach of these devices has been obscured by time. Archaeological fragments and scattered texts hint at systems once common, yet most designs vanished as civilizations changed and knowledge fragmented. Broken troughs, worn wooden spirals, and depictions in relief or manuscripts provide only tantalizing glimpses of the machine's diversity. Excavations at Egyptian irrigation sites and Roman settlements reveal traces of horizontal or inclined screws, but the precise methods, dimensions, and adaptations often remain conjectural. Scholars reconstruct systems through a combination of textual analysis, experimental archaeology, and mathematical modelling, yet even the most careful efforts capture only part of the original sophistication. What survives are hints of a technology that once blended practicality with invention, now partially eclipsed by centuries of loss. Engineers today turn ancient models slowly, measuring efficiency, marveling at precision, yet acknowledging that full understanding eludes even the most careful reconstruction. Laboratory and field experiments demonstrate that variations in pitch, angle, and diameter significantly affect flow, revealing the skill required to optimize each device. Observers note that even minor deviations in craftsmanship can dramatically reduce performance, a subtlety likely mastered by ancient technicians through experience. Despite these modern insights, many design variants remain elusive, their original purpose and refinement hidden in fragments or lost entirely. Each attempt to replicate the screw brings new knowledge while underscoring the scale of what ancient innovators achieved and what has since vanished. Countless screws must have existed whose operation and design have evaporated from memory, leaving only shadows in chronicles and ruins. Chinese south-pointing chariot. Even the most seasoned travellers could lose their way in the shifting landscapes of ancient China, where mountains and rivers offered no consistent guidance. For generals moving armies, messengers navigating vast plains, or officials journeying between capitals, the need for reliable orientation was pressing. Without landmarks or stars, finding true south could mean the difference between efficient passage and costly misdirection. It was in response to this challenge that the south-pointing chariot emerged, a mechanical solution that promised constant direction, yet whose inner workings would vanish from collective knowledge long before the machines themselves. The device was not merely a tool, it was a demonstration of the ingenuity and precision of Chinese engineering, a silent testament to a civilization attuned to both movement and measure. In workshops filled with bronze and timber, inventors transformed observation into motion, crafting mechanisms that defied conventional expectations. Historical records attribute the creation to the ingenuity of Ma Jun during the Three Kingdoms period, though its principles likely evolved from earlier experimentation with wheeled devices and directional instruments. The chariot was a mobile compass of sorts, a vehicle designed to indicate south regardless of turns or terrain. Its construction combined metallurgy, carpentry, and a keen understanding of motion, reflecting both scientific knowledge and practical skill. Every gear, axle, and lever was placed with intention, a precision hidden beneath the body of the chariot, visible only to those who understood the mechanisms at work. Inventors documented meticulous trials, adjusting wheel sizes, axle alignments, and pointer balance to ensure accuracy over distance, while contemporaneous texts hint at debates over which materials could reduce wear and friction. Some workshops reportedly built multiple prototypes side by side, observing performance across different terrains and road conditions, a testament to the trial and error approach that underpinned Chinese mechanical innovation. Beyond technical concerns, the chariot's design reflected broader cultural priorities. Precision, reliability, and harmony with natural forces were as valued as the practical outcome. These early experiments shaped a lineage of automata and mechanical devices, yet much of the methodology was transmitted orally or lost with the passing of dynasties, leaving only tantalizing descriptions for modern scholars. A concealed network of gears and wheels worked in silent harmony, translating movement into unerring orientation for the figure atop the chariot. The south-pointing pointer, often a figurative figure or stylized arrow, maintained its bearing through a clever differential gear arrangement that counteracted the rotation of the wheels. As the chariot turned corners or navigated uneven ground, the internal system ensured that the pointer remained aligned with magnetic, or in some interpretations true south. The principles involved rotational ratios and mechanical compensation, concepts that would not be formally described in Europe until millennia later. The device's elegance lay in its invisibility. It operated continuously, yet no observer could discern how it accomplished its feat without access to the internal mechanism. From ceremonial processions to strategic inspections, the device moved through courts and camps, its steady indicator of the South a silent emblem of authority. Emperors and generals used it to orient fleets, inspect fortifications, or traverse newly constructed roads, combining symbolic and practical functions. Beyond its utility, the chariot became a mark of status, a visible sign of technological sophistication and human control over the environment. Its presence reinforced hierarchies. Those who commanded the device held knowledge and authority, while those who observed its precise motion could only marvel at its apparent magic. In this way, the chariot served as both an instrument and a symbol, shaping perception as much as geography. Engineers tested different axle ratios and wheel configurations, seeking efficiency or portability, yet the full range of these adaptations has vanished. Some accounts describe scaled-down chariots, designed for private study or ritual use, while others suggest modifications that allowed larger vehicles to carry multiple figures or heavier loads. Experimentation extended to materials as well, with variations in bronze, iron, and wood influencing durability and accuracy. Despite these trials, the intricacies of many designs were lost when knowledge was transmitted orally or through fragile manuscripts. The ingenuity was tangible in its time, yet centuries of upheaval and technological secrecy erased much of the chariot's diversity from the historical record. Surviving texts and sketches offer only glimpses, hints of design principles and craftsmanship that no modern eye can fully reconstruct. Chinese chronicles describe the device's operation and occasional demonstrations, but diagrams are incomplete or ambiguous, leaving scholars to infer mechanisms from partial evidence. Archaeological discoveries have yet to yield a complete chariot, and while some replicas exist based on historical inference, these are approximations rather than faithful restorations. The fragments suggest careful engineering, but each new interpretation is a reminder of how easily knowledge can vanish when dependent on fragile transmission and specialized skill. The true complexity of the device remains elusive, suspended between documentation and imagination. Today, mechanists assemble replicas, turning wheels carefully to understand ancient ingenuity, but the original subtleties remain elusive. Reconstructed chariots reveal the principles of differential gearing, the challenges of aligning axes, and the balance between friction and precision necessary to maintain orientation. Even with modern tools and materials, engineers find that small misalignments can disrupt the south-pointing function, hinting at the extraordinary skill of the original creators. Experiments demonstrate the reliability of the mechanism, yet they also underscore how much tacit knowledge, techniques, tolerances and adjustments has been lost. Each recreated turn of the pointer is both revelation and reminder. The device's full mastery lies beyond our reach. As centuries passed, dynasties shifted, and the knowledge embedded in moving bronze and wood disappeared with them, leaving only fragments and conjecture. Phoenician purple dye process. Among the fabrics of antiquity, one colour outshone all others, its rarity conferring authority and awe. Purple became a symbol of power, reserved for kings, magistrates, and the most exalted of priests. Its brilliance and durability distinguished it from other pigments, while the difficulty of its production imbued it with almost mythical value. Societies across the Mediterranean coveted this hue, and possession of even a fragment of purple-dyed cloth signified wealth and influence. Yet the process that produced such a vivid colour remained cloaked in secrecy, a closely guarded, artisanal knowledge whose full scope would vanish with the decline of Phoenician cities. Along rocky Mediterranean shores, labourers collected tiny murex snails, each a reservoir of precious pigment. The work was arduous and perilous, performed on jagged cliffs or shallow tidal zones, where waves could sweep away both harvesters and their valuable catch. Estimates suggest that thousands of snails were required to produce even a small quantity of dye, demanding immense patience and careful handling. The mollusks were prized not for their size or flavour, but for the minute gland that secreted a fluid capable of transforming into deep, lasting purple when exposed to sunlight or heat. This reliance on a living source made production seasonal, localised and labour-intensive, ensuring that the dye's rarity would endure. Within workshops, artisans immersed shells in vats, using fire, time, and patient observation to release the vivid hue. The process required controlled temperatures and precise timing, with each step influencing the resulting shade, from reddish purple to deep violet. Although ancient texts describe aspects of the method, no full recipe survives, leaving modern scholars to infer the chemical reactions from observation and experiment. The colour emerged slowly, often after hours or days of careful manipulation, as the secret of light, salt water and enzymatic transformation combined to produce the unmistakable brilliance of Phoenician purple. Every vessel, stir, and sunlit exposure was a calculated act, balancing natural phenomena with human mastery. Rows of vessels and carefully measured ingredients reveal a methodical practice that required both dexterity and knowledge. Workers organised the dyeing rooms to optimise airflow, temperature, and the sequential handling of materials, ensuring that each batch achieved consistent quality. Such workshops were not mere production sites, but laboratories of craft, where observation and empirical insight guided each step. Apprentice and master alike followed strict protocols, and deviations could ruin entire batches, demonstrating the fragile precision of this lost expertise. Even minor variations in handling, timing, or material proportion could result in a colour that failed to match the prestige expected of royal or ceremonial robes. Purple textiles travelled across continents, exchanged for silver, grain, and influence, marking those who wore them as elite. Phoenician merchants transported the dye and finished cloth to Egypt, Greece, and Rome, embedding it within networks of commerce and diplomacy. Kings draped themselves in robes whose hue communicated authority, while city-states recognized its value in tribute and taxation. The scarcity and labour intensity of the dye ensured that it remained a marker of social hierarchy, entwined with both economy and ceremony. Its production and distribution were thus as much about cultural control and symbolism as they were about colour itself. Fragments of robes, inscriptions, and classical writings hint at a technology so valuable it was guarded jealously and recorded sparingly. Archaeologists have uncovered traces of purple-stained pottery, indicating vats and containers once used in dye extraction, while literary sources, from Pliny to Herodotus, provide tantalizing glimpses of the method. Yet the full understanding of the process, including exact chemical manipulations and handling of raw materials, is lost. Only partial sequences and descriptive references survive, a testament to knowledge that was preserved selectively and deliberately hidden from outsiders. Each artifact or mention serves as a reminder of human ingenuity now veiled in time. As cities fell and knowledge of artisanal chemistry faded, the precise methods vanished, leaving only traces in pigment-stained pottery. Workshops were abandoned, manuscripts decayed, and oral instruction failed to survive successive generations, erasing much of the procedural wisdom. Even when later civilizations attempted to replicate the colour, they found only an approximation, never the exact vibrancy or durability achieved by Phoenician masters. Modern chemical analysis can recreate shades reminiscent of the original dye, yet the techniques of timing, preparation and subtle manipulation remain largely speculative, an echo of lost expertise. Even with modern chemical analysis, reproductions of the dye reveal only partial understanding, suggesting the original craft has been lost to history. Attempts to synthesize the pigment illuminate principles and chemical reactions, but they cannot capture the nuance, scale or intuition of Phoenician artisans. The dye's story is thus one of brilliance and disappearance, a testament to skill intertwined with secrecy, a legacy of colour that reached across civilizations yet ultimately slipped through the cracks of time. The secrets of purple endure in shards of shell and whispers of vats, a luminous craft that history has almost entirely consumed. Sasanian wind towers. Caravans pressed on across sun-scorched roads, yet within Sasanian cities residents struggled to escape an unforgiving heat. Summers pressed relentlessly against the walls of mud brick houses, and the dense urban fabric of marketplaces and palaces offered little relief from scorching winds. In response, architects and builders devised a solution both subtle and extraordinary: vertical towers that harnessed the slightest currents of air, turning natural movement into living comfort. These structures were not mere embellishments, but practical instruments, silently regulating temperature while symbolizing the ingenuity of a civilization attuned to its environment. Scholars and builders experimented with vertical forms, translating the natural movement of air into architectural strategy. The earliest wind towers arose from observations of airflow over buildings and through narrow streets, refined over generations of trial and adaptation. Architects considered sun angles, prevailing breezes, and urban density, creating structures that drew air down into rooms and courtyards with remarkable efficiency. Historical records suggest that such towers were integral to Sasanian urban planning, blending functionality with aesthetic principles that demonstrated both mastery of craft and sensitivity to human comfort. Each tower stretched skyward, a slender sentinel above flat rooftops, divided into corridors and chambers that funneled the wind with careful precision. Some were square, others cylindrical, yet all shared the principle of channeling cooler currents from above into interior spaces. The internal partitions and angled openings were designed to slow, redirect, and diffuse airflow, creating a gentle circulation that lowered temperatures even on the hottest afternoons. The tower's height allowed them to capture prevailing winds before they were obstructed by neighbouring structures, ensuring that cool air could penetrate deep into homes and public halls below. As air entered the shafts, it interacted with angled surfaces and internal partitions, cooling the interiors through a combination of convection and controlled turbulence. In some cases, water reservoirs or wet clay surfaces were incorporated at the base of the towers, enhancing the cooling effect through evaporation. The flow was carefully balanced. Too rapid, and it would lose efficiency. Too slow, and it would fail to provide meaningful relief. These subtle adjustments suggest that Sasanian builders possessed a practical understanding of fluid dynamics, even if expressed through empirical observation rather than formal scientific theory. Beyond their functional purpose, the towers became a mark of status and ingenuity, shaping daily life in homes, markets, and palaces alike. Wealthier households boasted larger, multi-shafted towers, while public buildings employed them to create comfortable gathering spaces. The presence of wind towers signalled sophistication, blending environmental mastery with civic pride. Visitors would recognise a city's attention to comfort and innovation simply by observing the elegant silhouettes of towers rising above the streets, an architectural language that communicated both practicality and prestige. Builders experimented with cross-ventilation, supplementary water reservoirs, and variable shaft heights, revealing a subtle but now largely forgotten science of comfort. Regional variations emerged, responding to differences in climate, wind patterns, and urban density, yet most of these adaptations were lost over time. Some towers featured multiple compartments, angled openings, or internal conduits that allowed air to circulate even in complex building layouts. Each variation demonstrates a culture attentive to both experimentation and refinement, yet the details of construction methods, materials, and precise design calculations remain tantalizingly obscure. Excavated ruins and partial structures hint at the scale and sophistication of these towers, while fragments of inscriptions point to the skilled artisans behind them. Archaeologists have uncovered foundations, shaft remnants, and references in texts that illuminate the prominence of wind towers in urban life. Reconstructions reveal that even partial knowledge conveys a sense of precision and intentionality, yet they also underscore the gaps in our understanding. Modern engineers and historians can admire the ingenuity, but replicating the full effect of these vanished systems remains elusive, emphasizing how specialized and fragile such architectural expertise can be. With the collapse of cities and the passage of time, the expertise required to erect and maintain these towers faded, leaving only traces of a once widespread architectural intelligence. Political upheavals, economic decline, and the gradual abandonment of traditional building practices allowed knowledge to dissipate, while surviving towers decayed under the sun and wind. Even today, the full potential of Sasanian wind towers remains an unresolved puzzle, a silent testament to a civilization that understood and shaped its environment with subtlety and precision. Generations of wind and sun have passed over these ruins, yet the mastery behind the tower's invisible currents is still lost to the ages. Indus Valley Drainage System. Through the dust of centuries, streets and alleys reveal a silent logic, a hidden order that guided one of the world's earliest cities. Straight avenues intersect at precise angles, and uniform blocks suggest planning that exceeds mere necessity, implying a vision both practical and ambitious. The arrangement hints at a civilization attentive not only to architecture but to human movement, hygiene, and the organization of communal life. Despite the passage of millennia, this careful geometry endures, a mute testament to knowledge largely erased from history. Every straight line and measured corner carries the weight of decisions made with foresight that modern observers can scarcely reconstruct. Rows of perfectly aligned bricks and straight avenues speak of planners who envisioned both movement and utility, blending geometry with foresight. Cities such as Mohenjo-Daro and Harappa demonstrate consistent street widths, grid-like layouts, and intersections that anticipate drainage and accessibility. This level of standardization required coordination and oversight, suggesting centralized planning or shared architectural principles that guided construction across vast distances. Such foresight was unusual in the ancient world and positions the Indus Valley civilization as a master of urban organization long before comparable cities arose elsewhere. Even the alignment of buildings with cardinal directions indicates attention to natural forces and spatial harmony. Covered drains run alongside streets, their precision suggesting not improvisation but careful, repeatable engineering practices. Channels were wide enough to carry heavy flows of rainwater, yet covered to protect pedestrians and property. Bricks were carefully joined, and some drains featured vertical access points, allowing maintenance and inspection. The system extended across neighborhoods, connecting houses and public spaces to larger conduits, demonstrating a comprehensive understanding of how to manage water in both ordinary and extreme conditions. The integration of household drains into communal channels suggests a level of civic awareness and cooperation rarely seen in contemporary societies. Even private dwellings were equipped with drains and wells, a testament to concern for hygiene that would not reappear on this scale for millennia. Bathrooms and latrines were constructed to drain efficiently, sometimes connecting directly to street sewers. Wells provided clean water, and some homes had bathing platforms that suggest attention to personal cleanliness as an integral part of domestic life. Such practices indicate not only technological skill but an awareness of health and sanitation that was centuries ahead of contemporary societies elsewhere. The coordination between water supply and drainage reflects an understanding of contamination prevention and water management that modern engineers would admire. Bricks laid in uniform dimensions and carefully sloped floors indicate mastery over materials and a subtle understanding of water flow. The use of standardized fired bricks suggests both durability and planning, while slopes in channels allowed gravity to carry water without stagnation. Artisans achieved precision without the benefit of modern surveying tools, relying instead on empirical knowledge and consistent technique. Every aspect of construction, from angle to alignment, was designed to ensure that water moved predictably, preventing flooding, contamination, and structural damage. Even minor miscalculations could have disrupted the delicate balance of streets, drains, and homes, yet the system functioned for centuries. Such infrastructure shaped daily life, offering convenience, health, and perhaps even a subtle reinforcement of civic order and responsibility. Citizens could rely on functional sanitation, reducing the spread of disease and facilitating dense urban living. Public baths, communal wells, and regulated streets likely encouraged social interaction under hygienic conditions, strengthening community cohesion. In this way, technical expertise extended beyond practicality, shaping both behaviour and social norms, and revealing a civilization that valued both innovation and the well-being of its inhabitants. The presence of such systems may have also allowed cities to support larger populations than most contemporary settlements. Fragments of drains, wells, and public baths endure, yet the principles behind their design remain largely inscrutable, leaving questions about the civilization's knowledge and intentions. Archaeological evidence provides clues but rarely the full picture. Much of the engineering logic was lost with the decline of cities, and written records, if they existed, have vanished. Modern scholars can trace channels, measure slopes, and reconstruct partial systems, yet replicating the seamless integration of streets, homes, and drainage remains a challenge, underscoring how easily complex knowledge can vanish. Each excavation uncovers small hints of a network far more sophisticated than most ancient civilizations would achieve for centuries thereafter. The Indus Valley's mastery of urban sanitation stands as a silent enigma, a blend of practicality and foresight now obscured by centuries of time.